Welcome to Hot Chips 23. Tutorial 1. Package Scale Power Management.
Program committee this year, when we were looking for which tutorials to have, we realized that power is a overarching concern in all kinds of chip design these days, and in particular, people are interested in the different trade-offs between having different voltages on the chip, and how do you get multiple supplies there, and how do you do this inexpensively? And so, realize this would be a great thing to go out into industry and find experts to give us presentations on what's happening, what's the hot research in those areas. Fortunately, I could think of immediately of my colleague across the street, Elad Alon, UC Berkeley, and I managed to tap him to actually do all the hard work of organizing and bringing together a great set of speakers for the tutorial. So I'm going to hand it over to Elad to introduce the speakers. Okay, thanks.
So thanks, Kirsta, for giving me the opportunity to organize this. I think we do indeed have a great set of topics coming up for you. So let me just dive right in and go ahead and introduce the first speaker. So Steve Kosonocky, and why don't you come on up, is from AMD. So he received all three of his degrees from Rutgers, spent quite a bit of time at IBM TJ Watson, so about 13 years or so, before moving to AMD in 2007. So he's now at AMD in Fort Collins and is interested in many of the topics that we'll be discussing today. So things like practical power gating, how you do dynamic voltage and frequency scaling, as well as generally energy efficient CPU and GPU design. So that, I'm going to go ahead and turn it over to Steve.
Thank you. Okay, I guess just waiting for the presentation to go up on the screen. Okay, so I'm going to talk about some practical considerations for power gating and dynamic voltage and frequency scaling. The outline of my talk this morning will be first go over a little bit of motivation for DVFS and power gating, and go into a little more deeper details of how we do some dynamic voltage and frequency scaling, then look forward to some forward topics in there in regards to embedded regulation, some issues there, and mini-core applications in the future. Then I'll switch gears, talk about power gating, go through some of the issues in power gating, some of the things that we do to make that work, and then end with a conclusion. So let me start with the motivation. So what are the key motivations for all of this is really power and the fact that performance is really power limited. And then also cost for things like servers. And in the server area, the server compute capacity is per dollar is increasing steadily. And that's driving up the total power per dollar spent on servers. So if you look at the graph at the top here, the server power is just increasing per $1 million worth of spending of server is just going up and up and up each year, and we don't expect that to stop, especially with the increase of all the handheld mobile devices that require server capacity to make those really effective. Also driving up is the cost of electrical power spending. The price of oil is going up. We're looking towards more green alternatives, and that's could be more expensive. So the server cost, the cost to power the servers is going up each year. And if you look at some of this data on the bottom, the spending for $1 million, the total cost to power $1 million worth of servers is actually more than the cost of the servers themselves, and that just kind of broke there the $1 million mark somewhere about 2010, roughly. So we see this as a big motivation to do more in terms of lowering the power. The next other areas is the green initiatives. Of course, we don't want to drive up greenhouse gases, and we like to do as much as we can to save energy and reduce costs. For the mobile and desktop, there's a high degree of integration of special functions. In this area now, there's a lot of new diverse workloads coming in and more capability in a smaller form factor. These diverse workloads have lots of data serial, data parallel aspects to them, streaming. The compute could be very intensive in bursts, and then there could be long periods of inactivity. Also, of course, it's a very small form factor. We want very long battery life and instant access to the device. And autonomous power management. We don't want the users to actually do anything. It just wants to be low power all the time and very high performance when you need it to be. And you can see some of the things that we see now. We're moving towards HD video, flip cams, phones, webcams, 3D internet apps, 3D Blu-ray, multi-touch, facial gesture, voice recognition, mouse, plus the mouse and keyboard, and we want all-day computing. So these are some motivations for doing things like DVFS and power gating. The other one, if you look at just the basic performance per watt, if you look at Fmax as a function of voltage, you see that we get some good increase in Fmax as we scale voltage up. And that's one of our biggest levers for increasing performance on demand. So we want to take advantage of that, but at the same time, the power increases very quickly. And we don't want to stay at that highest voltage for too long. So if you look at the performance per watt, it's really maximized at Vmin, and we want to get down there as fast as possible and stay there and stay as close to that point when we don't need the peak performance. So that's some of our motivation here for scaling voltages. If you look at the total core power, and I have to apologize, the slide in your handout actually has an error in there. It's plotting the sum of these with a stacked bar graph. So the updated slides will be distributed on the website. But so if you just cross out that yellow bar for total power, it's the same slide. But here, what you see here is the leakage could be up to 40% of the total power. And that's really good motivation for trying to do power gating. That leakage is there. If we want high performance, typically that's the realm we're in. It could be 30%, 40%, but in that region is typical for most process nodes. So to deal with this, we really have, as mentioned, really two knobs have emerged for controlling all this power. One is dynamic voltage frequency scaling, where we really want to optimize performance for the application while it's running. And the next one is power gating. And here we really want to gate the power during the idle periods. And each of these knobs really presents a unique challenges for implementing them efficiently and optimizing those functions. So let me dive into DVFS here. So in our APU, or Alon Accelerated Processing Unit, one of the key things this chip offers is high performance on demand. By integrating the GPU with the CPUs, we eliminate power and latency of the extra chip crossing. We get 3x more bandwidth between the GPU and memory, and for the same size GPU is substantially more effective. And power efficient and advanced technology for both CPU and GPU can be used. And then it also allows us the opportunity to have thermal management, dynamic thermal management between both the CPU and GPU to keep the overall thermal budget in place. Some of the key features for Mobile Mark 07 here for the Alon processor is really lower idle power and active power. And it includes DVFS, clock gating, of course, and power gating of the key functions. And also a robust and flexible power management control system. And then if you look at the power breakdown, you can see that for typical applications, CPU is about a little bit more than 25%. You have the GPU, you have the PHY, the North Bridge, the analog, and the I/O PHY. So all these contributors are very important for the total power consumption. It's really important to reduce all these functions as much as possible and only power things when you need to. So in that sense, we look at here, this chart shows the APU power management for Llano. And you can see we have a number of policies for the DDR-PHY. We have self-refresh. We could pre-charge or power down or turn the PL off. We could change the speed. We could reconfigure the physical interface, the I/O. We have the link width, link suspend, PLLs off. We could do a link rate change. And then from the driver, we could power these down as well. At the CPU side, we use DVFS, deep power down modes, PLLs off. We could change the max P states, processor states, and then for boosting capabilities, we have DVFS. And then in OS control, we have P states and halt. On the GPU side, again, we have DVFS. We have throughput scaling capabilities, power down modes, max P state as well. And then we could boost the voltage and frequency for higher throughput scaling. And of course, we have power down modes controllable by the driver. And then again, for the North Bridge, we have DVFS capabilities, power down modes, max P states as well, DVFS, and then we could set P states through the driver functions as well. So all these policies are really a holistic combination of hardware policies and OS interaction and driver interactions to optimize the system dynamically on the fly. So dynamic voltage scaling, how does that really work? What does it really mean? So, oh, sure. I'll take questions. Oh, excuse me, yeah, can you go to the microphone, please?
So you're taking questions as we go.
Sure.
Right? Okay, so the P-state concept and maximization of P-state in your policy, can you describe a little bit more of the details of that? I'll touch on that in the slides coming up, hopefully, and if I don't, please ask, I'll revisit that question if that's not satisfied. I'll go through that a little bit. So let me go on here to the P-states. What does that mean here? And that really, what those define are voltage frequency pairs that match the frequency, that are set to match the frequency operation with the workload on demand. And we try to use the lowest voltage to sustain the required frequency here. And so we have a number of P states that are defined, both controllable through the OS and underlying hardware mechanisms that are automatically adjusted on the fly to boost this performance when it's needed. And then we can then go into different C states, which are really states for degrees of idle control here that include things like halted cores that will ramp down the clocks, and then also maintain cache data or else store that data out into the main memory. And then we could also power down the whole core through power gating and then come back up quickly. So one of the key aspects here for DVFS that we've done is to really design for that. And this is, again, I have to apologize, this slide is not included in your handout. I just added it. I thought it was an interesting one, but it will be included in the downloadable copy you'll have access to. But the key point I want to make here is that when we do implement DVFS, we really want to optimize the timing across that entire voltage range. And what we've done for the bulldozer core was really two voltage corners that we timed to, both at 0.8 volts and 1.3 volts. And when you compare how the timing was to an older core that was not tuned for full DVFS range, we've got a lot more frequency benefit at the lower voltages and the higher voltages for boosting states. So we've really made a lot of effort by those two voltage corners for tuning the frequency tuning. And by doing this, we're able to both work on gate-dominated paths with high RC and paths with high RC content. to provide that scaling across the voltage range. So let me go back to some of the DVFS and how that's implemented here. Hopefully this will answer your question. And if not, I'll try my best, or else we could take it offline afterwards. So for DVFS, what we're really trying to do is for low power applications run at the higher voltages. So how we do this is we have a chip level power estimator, and that estimator then is combined is used to generate a thermal history representation of the chip. And with that thermal history representation, we can then trade off power credits between the CPU cores and the GPU SIMD units. And basically how it's done is on each of these sections, we have special hardware counters here that are used to count the activity or to track the activity of the GPU or the CPU. And then we map that into a power level. And then we have a global manager that then trades off these power credits to cap the overall thermal or overall voltage, overall thermal budget to acceptable levels. And so if you see on that little chart here, basically what it allows us to do as well is if we have power credits from, let's say, the idle GPU core or the CPU core, we can have small burst periods of boosting capabilities where we could boost the voltage above the TDP limit at small periods of time. So because of the long time constants for the chip to actually thermally heat up, we're able to get a little bit of higher performance at small portions, then scale back if we see that thermal limit starting to increase too quickly. So the basic algorithm for DVFS is really inside that state machine here in the North Bridge here that does the overall power management and trading off these power credits. So how does that look? If you look at a thermal map profile of the chip. So this is showing a CPU-centric workload where you can see the 4 cores in a Llano chip having higher temperatures than the GPU. And then if you look at, let's say, a GPU-centric workload, you see the GPU actually having higher temperatures, and the CPUs are down lower, and we're able to boost up in these pictures, for example, the GPU voltage and frequency, and take advantage of the fact that the cores are idle. And if you look at it like a balanced workload, where the thermal budget is actually more evenly distributed across both the GPU section and the CPU section, you see that we're able to manage that with the on-chip control. So what happens when we have more cores? So far we're looking at 4 cores, graphics. We're already at 6 supplies, 2 high current supplies. We have a VDD supply that services the 4 cores. We have a VDD-MB supply that services the graphics North Bridge. Then we have some of these miscellaneous supplies like IO, VTT, and VDA that are used for special functions, analog, and the PHYs. And what happens if we start adding more cores or more accelerators? How do we handle that? It becomes an issue. So let me go through some of the issues there for scaling out, how this would play out that we're facing. And one is package limitations. We can't just add more supplies and bring them in through the package very easily. And this is just kind of an example picture of what the package layers look like. Typically, you have like in low-cost packages, you have 4 thick layers of high current power or current capability layers for distributing the power across the die of the chip. And then there's 3 to 4 buildup layers on top and below that that are used to interface down to the chip at high density, and also for signal routing out to the pins. And these are typically used also for secondary supply and signal routing to the pins. So if you just look at this, if you were to add more high current supplies, you're really adding cost to the package to support that. You've got to add more of these thick layers to really distribute that efficiently across, and that gets expensive. if you look at how this really looks like on die, on the left, you can see one of the planes here showing the VDD distribution plane being shared with a VDD-IO plane. And you can see there's some limitations here in terms of how you effectively manage those power planes in a package. And because of that, it actually causes some limitations in terms of the voltage drop across the die there. So, and then also on the left, you see you can see the package capacitors. Those are placed around, and for noise reasons, we really want to maximize how many capacitors we could put in a package. But for space reasons, we're really limited there. And here you can see, we're pretty packed in there. There's a certain keep out region where you can't pack these capacitors too close to the die for mechanical construction issues. But we can't just, if we add more supplies, then we have to add more capacitors in there too to support the supplies. And that becomes very hard to manage. So adding more high current supplies is very difficult. Then of course on the right side is showing one of the routing layers here, and you can see that's really packed. We can't, if we're just to add some more supplies, we're stealing layers, we're creating more via pass-throughs that have to come up to feed those supplies. It makes it harder to route all the signals around. So it gets very difficult. If you look at just the picture there that I showed with the VDD core versus the VSS, if you look at the droop across the die, assuming a uniform power distribution on the die, you can see that because of the fact that VSS has more resources in a package typically dedicated to it, we get a more uniform voltage drop in VSS than VDD. And what this is showing here is because we were bringing VDD in from the left side, mainly because that's where the pins were located. We actually see a little bit higher droop across the die, and that's what this is showing on the left side. And on the right side, we see the VSS is much more uniform across the die. But what's not shown here, the Y scale, of course, but the droop on the VDD side is actually 2.4 times higher than the droop on the VSS side. And that's really because of the fact that we just don't have as much resource dedicated to that distribution. So if we were to add, another supply there, a secondary or a third or fourth VDD supply for each of the cores, what will likely happen is we'll be robbing more resources there to keep the cost down, and the droops will get higher. What does that VDD actually look like on die? This is a simulation of an x86 core with a packaged board model here, running DGEM benchmark trace. And there's a little bit of a first initial noise, a little bit of a startup simulation noise that happens when you, in the simulator, when you just start it up cold. The simulator tries to prime the inductors. So if you neglect the very first startup noise, you see actually about a 50 millivolt ripple in the VDD supply. And you see the current is just pounding away, and this is normalized current here of the core, just pounding away, running DGEM, one of our high power applications. And so those supplies, they're not stable at all. They're really moving all over the place with noise. And this is kind of a typical noise that we would see on the processor. And there's only a few knobs really to counteract that noise problem. One is to try to increase the local decoupling cap, but I already showed that we're pretty much limited already. We try to put as much as we can on the package. And the other one would be to add local decap. If you look for other places to put decap in a package, some people put them down on the back side of the package. And when you look at that, putting them on the back side is much less effective than putting them on the top of the package like I showed before. If you put them on the back side, you have to drill down through the vias to get to that capacitor. And that high impedance path adds more resistance in front of that capacitor, making it less effective. So having capacitances on the backside to make them really effective requires lots of resources in terms of the vias to get down there to lower that impedance. So that's one of the considerations there and where to place those. The other option would be something like trench capacitor. If you could do something on die with a very high K or very large amounts of capacitance, that could help. And this is a plot IBM showed for the Power 7 chip where they added trench capacitors where the capacitance per unit area is about 25x that of thick ox. And that could be an effective means for really adding capacitance on die where you need to. But the disadvantage here is that it does add significant cost to the overall chip. So for kind of very high performance, low volume, expensive chips, this is a great solution. Very low cost, mobile, high volume. This becomes problematic, and it just goes into the bucket of overall trade-offs. So I talked about kind of conventional issues here with bringing supplies onto the chip. Next, I'll talk about possible, what can we do to integrate some of these voltage regulation, and we'll talk. And Elad will talk more about the switch capacitors in his talk, and Don will talk more about some of the inductor research that he's doing. But I'll just kind of briefly mention some of these other opportunities, and some of the issues here I see going forward. So for integrated switch capacitor regulation, that would be really nice to get that in there close to the chip so we could try to have a very fast regulator. For a switch capacitor, the most effective step down is really a 2-to-1 voltage conversion, because that really makes it much easier to switch the flying capacitor in and out with low impedance and low losses. And there's a paper by Leland Chang and IBM that showed using trench capacitors for the switch capacitor at ISSCC in 2010, or sorry, VLSI Symposium in 2010, showed a 90% efficiency for a 2-to-1 step down, but then it drops for other ratios. Then when you see other papers, they're somewhere in that range where some of the best ones are a little bit over 70%, and they're climbing up to around 80% in the future, with more advances in circuit techniques and technology. But that's kind of the realm you could probably get in switch capacitors on the chip. And the key thing is they do require very large capacitors. And if you have something like a trench capacitor or some special capacitance for that helps a lot. The next one is there's also a large voltage and current ripple associated with that. And that you can really mitigate with something like a very large capacitor outside, again, to help smooth that out. Buck converters. There's a lot of papers coming out now on integrated buck converter designs. And if you look at those papers, one of the key aspects to make them effective is having some special magnetics. And I think Don will talk about that in his talk. But if you look at trying to do this on die with existing air core inductors, it becomes difficult to make a high current inductor with the typical thick metal layers available on conventional CMOS processes. And one of the studies I looked at is, you could get something around 0.3 nanohenries possible. Much higher than that is difficult. You could reduce some of the inductor requirements by running very high switching frequency, but that could increase your losses. And then the key problem here is really the parasitic series resistance of the inductor, and that I²R loss there. And you could try to fix that or tackle that by multi-phases or parallel regulator architectures, where if you could reduce the current, then the I²R loss gets reduced very quickly. But even there, that presents problems here without having some special process hooks to help solve them. This is just looking at a plot on the left here is looking at some discrete inductors from a company a few years ago that they published in their data sheets, Coilcraft. You compare those to a CMOS, the DCR or the DC resistance of the inductor is much, much lower because they're using special materials here for the inductor. Whereas if you did this air core, the resistance is much higher for various inductor sizes. If you look at efficiency, if you just look at kind of peak efficiency where it's gauged by the I²R loss, here, to get above 70% for different TDP power levels, you really have to have many parallel regulators or buck converter phases, no matter how implemented, or some combination of the two, to get above that. And it's really looking at 25 or more, or up to even 85 or so in that regime to get at let's say 15 watt TDP or 20 watt TDP to make that efficient there. So that's challenging by itself. If you look at linear regulators, basically they work, the error is divided between the output and reference voltage, and it's fed back to a pass transistor to correct the error. And the transistor could either be an NMOS type for higher performance, so it's kind of a source follower output, or a PMOS, low dropout. The efficiency is really only good for small V in minus V outs, where the efficiency is roughly equal to the output voltage divided by the input voltage. And so if you have a low drop there, you can get actually pretty high efficiency. The LDO can be more efficient, the PMOS output, but there are some speed and stability impacts there that are hard to manage and it could become an issue. If you look at the PMOS style, you basically, that fed is a PMOS, and some of the challenges here is really the bandwidth of the system has to be very high to deal with the demands of a modern processor, where it has to be at least a gigahertz type bandwidth, or else you need a very large decoupling cap on the output to deal with those transients that we see in processors. And that's very challenging with a feedback design system like this. If you look at an NMOS style, you have that source follower, and that could react fairly fast. Some of the issues here is, again, you need this high bandwidth response, but it tends to be react faster with the source follower. But you do have this drop with a VT across the device, so you need some sort of charge pump or something to bring that voltage up on the input. And that could hurt your efficiency, or you could need some special devices there to lower that VT down to 0 or something like that. Another method that's people are publishing in the research area. Here's one I picked out. There's a number of people looking at this. One from UC Davis here, from Bevan Bass's group here. He showed a fully integrated 167 processor system where each tile in that system is an independent has an independent clock and voltage. And basically what they do is they distribute two voltages, a high and a low voltage, to each of these tiles, and then they have a local oscillator, and then they have this controller, DVFS controller, where they're basically switching back and forth between those two voltages on demand. And that's a nice way here, what they're showing at the bottom, a way of getting that DVFS function, but with just two fixed voltages here. And that's a very interesting approach, I think, too, going forward. So that kind of wraps up some of where I see the directions are and some of the issues going forward, looking at different applications or different ways of implementing DVFS in kind of future systems. Now I'll talk a little bit about power gating and some of the impacts there. So what's the problem with power gating? Why is it interesting? Why is it not just trivial? There's really a lot of choices there on how to do that. And you need to really analyze the particular function you're going to power gate. And some of the considerations here are the design complexity is a big one. Adding the power gates in the design, unless it's a fully automated approach, does add a lot of complexity to the design time and could impact schedule. There's power savings, how much power savings you get from doing this. Frequency performance impact. You always have some IR drop across that power FET. You have some wake up time. You have area overhead. Verification complexity is probably the biggest one. One of the biggest hindrances of how to put this in efficiently in local places. And then, of course, all this rolls up into ROI, or return on investment. All right, so power gating, just quick definitions. During active mode, you want to have you naturally have a low gate activity factors in your chip, which allow you to effectively share that power FET over time, so that power FET doesn't have to supply the max current of all your devices switching simultaneously, because that actually never really happens. In our modern processors, our clock gating factors are on order of maybe 10%, 15%. And the actual data switching factors at the gate level can be down to like 1%. So that's where you really get a lot of the efficiency in power gating, because you're not really sizing that FET for 100% of your gates all burning out at the same time. You're really sizing for like 1% or so of those gates switching at any one point. So that gives you a big savings in terms of area of that gate. And then the other one is you want to minimize the resistance of the cutoff device. That's key. And then also some of the penalties you have is this increased logic delay, and which you could attack by either a higher external supply or run at slightly lower frequency. And I define some terms here where V logic is the voltage across the logic, and the VIRPG is really the voltage drop, the IR drop across that power gate. Then during sleep modes, we really want to maximize the off resistance of the cutoff device and then reduce the standby power that way. And we could get reductions of 10x to 1,000x. And really, and that trade-off really depends on how much IR drop you want while that FET is on. So typically, I'll show 10 to 20x for high-performance processors. You've probably seen papers for mobile devices where they get 1,000, 2,000x, but then they have higher voltage drops during on periods because they don't really care about the active or the peak frequency as much. And then of course you could have noise when you transition to cutoff, and when you transition to cutoff, you could have very high sleep currents. Then all of a sudden you turn off the power FET and you get low sleep currents. If it's 1,000x lower, then that could generate a DIDT event. But the bigger DIDT events really in the wake-up mode, where when you turn on the FET, all the capacitance that was discharged underneath that power FET needs to be charged up. And if you turn on a very low impedance switch, it could charge up very quickly. And if you just kind of do a first order analysis, the peak wake current could be estimated by this simple equation here, where you're just throwing on all the devices at wake time at first, and you have to charge up that VDD across those capacitors all at once. That could be very problematic. We look at Llano, some of the early hardware. What we saw is some measurements, and this was published in JSSC last year, or in January. You can see actually we get over 20x leakage savings by power gating, and that's very, very effective way. So we could really essentially get no leakage, because once you get down to that low amounts, there's very little power there. So effectively, it looks like nothing. So we've wanted to determine the frequency impact during active mode. Kind of give a little bit of a formula here. It's really the easiest way is to derate the timing models and target a fixed maximum value for that voltage drop, and then design to that fixed value. And then there are some second order effects here in terms of circuit area growth could hurt you, wire blockages by the power FETs. They tend to need a lot of resources to get up into the upper levels of metal, and then also decreased availability of quiet decoupling capacitors. So when you power something off, you also cut off that capacitance. So that capacitance is not available for decoupling for other blocks that may be running. So that's an issue as well. If you look at the frequency impact, just from RO data, if you use a ring oscillator to estimate your frequency, what you see is for roughly a 1% VDE loss, you get about a 1% frequency loss right around your supply voltage. And so it really, when you look at a high performance core, having like a target of a 10 to 11 millivolt drop at like say 1.1 voltage, 1.1 volts voltage level, that's a reasonable level to expect for your drop across your power FET during design. How does that power FET look? It really, that FET when it's on, it really looks, if you look at the IDS versus VDS and then convert that to RDS, to resistance, it really looks like a linear resistor in that small region of operation from 0 to, let's say, 50 millivolts. A resistance model is a very good approximation for how that FET works. So you could basically use a resistance model in determining what the drop is across that FET, and then add it to your supply, basically simulations. And so for a target operation, let's say 11 millivolts, we're kind of right down along there where that's the drop level we expect for a lot of our power gate designs. How do we do those designs? One of the ways we do it is we can either embed them in rows or checkerboard style. And when we do that, we're basically, the current flow, what happens, it has, let's say if we have a standard cell rows, here I'm showing a bunch of standard cells, then they get interrupted with these power FETs. We have to pre-populate the rows first and then place the standard cells in, and then the current has to then flow from the standard cells up through the power FETs, up to the upper levels of the chip. And we by planning that, we can't travel along those low-level metals too long before we get too high of our drop. So we had to look at that and analyze that ahead of time. And so one of the ways you could do that is simply construct a simple resistance model here. And if you look at, let's say, a uniform current density and split that out across your region, you can calculate how many rows you can effectively have and stay within your IR drop limit. So if you plot those out, it looks like something reasonable and reasonable technologies for kind of a 1 amp per millimeter square current density. You get about 30 rows before you need to put down another row of power gates. And if you change that power density, then you could go longer. But that gives you an idea of how often you need to put those in and what that would do to your area impacts, area overheads for the design. The other limitation you have to think about is EM, or electromigration. If you squeeze too much current in, that could be a problem, especially at low levels of metal. So you need to give some high-level metal resources to spread that current around. And if you look at, in this plot, if you look at some of the 1x or 1.3x metals that we typically use at AMD, if we go to that 30-row limit, we're well below our EM limit, and that's pretty good. But if you were to have some other higher current densities and relegated to just very low levels of metal for spreading it, you could have a problem there. What happens in that problem, you basically, if you look at kind of the vertical cross section here, you have this grid, and if you use hierarchical metal structures, some of that metal power grid is just dedicated to virtual VDD, or it could be dedicated to the real VDD. And if you have to get down, basically down into the power FET, you can very easily get some EM problems at the lower levels of metal there. And some of the things you can do to mitigate that is really careful structuring, where you could maybe cut some of those low levels of metal judiciously right around your power FET, so that forces some of the current to go through the upper levels of metal. And that's some of the techniques that we use. This is just an example of a GPU tile, what the power gates look like. The power gates are in a checkboard style. I can't see them too well here, but they're in red here, spread all around the chip. And then there's a whole bunch of always-on cells, and they need to be placed inside your design too for cross-chip or cross-region buffering when wires go across. You also have a bunch of wires or regions on the sides. Let's say you have this tile that where you need to put protection or what we call isolation blocks to isolate the outputs, so they don't, when they do get power gated, they don't keep propagating unknown states down to other blocks. Then of course we have SRAMs, so you need to squeeze the power gates around the SRAMs or inside the SRAMs here. So those are some other issues that you have to go through. If you look at the drops there for this power gate, this is using a simulator, Apache Red Hawk, where we look at what the drops on the VDD grid. Sorry, in this example, we actually have VSS gating here. And you can see that the voltage drop is across the power gate is roughly about 10 millivolts. There's some regions some of the power FETs have a little bit higher, some are a little lower, depending on how much local current they have. And then you see the overall supply, the VDD ground IR droop here is higher. And so when you do add power gating, it will tend to spread out that yellow, your overall supply droop, and give you a larger distribution. So that'll impact your overall top frequency, because that distribution of drop across the grid will essentially get bigger. The other style that we use is the external ring gating style. And here we basically cut out the macro or core and then put a big power ring around this. And when you do that, that has a lot of implications in terms of IR drop, because now all the current's feeding from the edges of that core. We actually do this in the x86 cores in Bulldozer and Llano, or in Orochi and Llano. And here we have a ring that rings around the entire core. And one of the key things, that, considerations here is how do you spread that current across that core efficiently? But by doing this ring style, it does make things a lot easier on the design side, because now the CPU design really doesn't have to know anything about power gating. You just do it as normal, and then you just plop it in and put the ring around that. So things like timing and verification becomes much, much easier for the CPU team. But to deal with this, we came up with a novel approach here where we're using a package layer, actually, where we take some of the very thick metals in a package and use this as an assist layer to spread the virtual ground. In this case, this is showing a picture of Llano, where we spread the currents out. And this is actually the diagram on the left is just a cartoon of the actual core. It has a few more bumps. I just didn't want to draw all the bumps in there. But it basically has this power gate ring that goes around the core. And what we do is the normal VDD bumps, VSS bumps, are attached to the package in the middle of the core, and the current actually flows up in through the package, across the sides of the package, or across the sides of that layer there to the edges of the core, then back down into the power gate ring, through the FETs, and then back up through those red bumps there into the package, back into the package and out onto the board. And you see the kind of the cross section here, that little green diagram. Let's grab. So if you look at this, you see, this is the path the current goes. If you look at the effective resistance of that whole path, is about adding 1.1 milliohms resistance to your supply. And you could use that number to then, for kind of high-level estimations of how much frequency impact that would have to your core or power impact. Then on the top graph is really an IR map of the simulation for a particular workload, and showing kind of a cross-section. If you just make a cross-section across this IR map, this is the percentage of the drop where it's going. You see a lot of the drop is over here near the execution units on the side here of the core. And the overall drop of the footer is pretty low, but then you still have a lot of metal IR drop across the metal distribution getting up through the C4s and the VS, up to the footer, then back down from the footer on the other side there. So there's a lot of challenges to do that. And one of the challenges here is when you do the spreading, you're basically spreading all your current and funneling them down through a few bumps now, right on the periphery of the core, and you could get bump EM issues. Okay, so to deal with that, if you look at the picture on the cartoon on the left, if you consider these two package planes, where the one shaded one in gray is the virtual core package plane, and the beige one is the SoC package plane that represents the real VSS. We're basically taking the current and going down through the chip back up. If we have just kind of this uniform interface, we could get some hotspots, some bumps could show possible reliability failure. So came up with a solution where we created this kind of a zigzag boundary. And what this does is allows us to place more kind of VSS bumps right at that periphery, or extend the periphery to get about 1.5 times more peripheral C4 bumps at that boundary. Then we do a lot of very careful engineering to balance the resistance to those bumps so they look equal electrically as much as possible. So power gating opportunities. We really want to maximize the opportunity for power gating here. And we'd like to, if you look at power gating, we have certain burst parts of in the application where sometimes we're running the application going idle, running an idle. And some considerations here is the energy break-even point, the inrush current, and time to restore the power gated region. I think about 13 minutes. Oh, okay. So This slide really talks about the energy break-even point, and that's one of the considerations here. And you have some overheads in terms of turning on the power gate, then turning them off, and then you don't get the savings right away. And at some point, you get some break-even point in the energy. And that's one of the key issues that you want to use or consider when you're deciding what blocks the power gate. The next one is inrush current control. And inrush current, when you turn that on, as I mentioned before, you can get a huge inrush of current, which can then cause a lot of noise, DIDT noise. And some of that results in, let's say, supply bounce. It could cause EM violations. Short circuit currents, as it's charging up, could imbalance some of the nodes and cause some reliability errors. And you can actually destroy state nearby. This is just a simple model of looking at some of the inrush currents. You can think of it, you have these inductances in the supply and the ground. Then you have these different power gates regions that could be turning on and off and generating noise on the supplies. As I mentioned before, you can disturb retention flops, JSON IP, SRAM. One of the ways you get around this that we use in Lano and Rochi or the Husky core and Bulldozer cores is really, we created this finite state machine to gradually turn on the power devices in a controlled manner, and then made that fuse programmable where we could change the strength of those devices or the duration of them turning on in terms of groups, so we could successively add more current more gradually, and then use that and tune that post-silicon in a post-silicon method. And this is just an analytical model here showing how that works. And it's just an RC model showing where when we first turn on the first group, we could get this inrush of current. It starts to reduce the supply, or in this case, it's VSS gating, so it's charging up the capacitors, the ground-plated capacitor down to ground, and we get some good charging, and then we turn on the next group, gets more charging, and while it's charging, it's battling the leakage as well, so we have to have enough FET turned on to overcome that leakage current as well. Then as we turn on these groups, we get closer and closer to fully charge up that capacitance. Then at the end, we could turn on the full group, and then everything is charged up. If you look at kind of that first step here, this is, again, a Red Hawk simulation of Lano, one of the cores, and we could see up to about 3 amp peak here in one of those programming settings. And we could change that so we can make that peak very large or very small. And when we look at the hardware, some of the results of that is the distributions on the left show where CC6 mode is when we turn something on and off. If we have the left set of dots represent cores one core going in and out of CC6 while 3 cores are running a max workload. We're checking the max frequency. Then from that we could estimate what the voltage, transient voltage effect of that one core going in and out of CC6 is on the other cores. And if we turn all 3 cores, let's say, to go in and out of CC6 and use one core as a kind of a voltage monitor, we could see a pretty large transient drop there. But if we go to a small inrush setting, we actually don't see that drop anymore. And then we see that if the frequency is really limited just by the number of cores running the max frequency. So that becomes a non-issue now because we've taken away that transient issue there. State, save, and restore. There's a number of ways that have been published to do this. You can regulate the virtual supply during a sleep mode to low voltage. This allows you to save the state at very maybe fast wake-up times. You don't have much of a penalty for getting the state back. You can use retention flops. That's got some area impact there and has some impacts in terms of how do you power those retention flops. Or you can write out the critical state to memory using a serial parallel path. And that's actually what we do currently in our APU designs, where we write all the state of the core out to the main memory and then shut them down, then restore that state. And that actually, you can utilize a scan mechanism to do that, and has a very low area overhead by doing that. But it does have some impact in the total time of going in and out. So, conclusion. Overall, DVFS really provides a nice capability for optimization of the CPU, GPU, or APU performance per application. As we add more cores to the IP and SoC, it'll become more difficult to do that. We could use power gating as one way as we do now, where we have a set of cores on a common voltage that we move up and down, then we power gate these individually. That works. At some point, you may want to look at an integrated regulation scheme. That could be another effective way of tackling the problem. There is still a lot of open issues around that. Power gating, it's shown that the maximum frequency impact is very minimal. You could do this by embedding in the IP or surrounding by ring. The opportunity is limited by the energy break-even point, the inrush noise, the time it takes to restore the state overhead, so that limits how fast you go in and out. And one of the key things is inrush current control. That's kind of one of the key limiters for, as well as the state restore for how quickly you could go in and out of power gating. So I'd like to maybe open up to more questions.
So the large the voltage drop component in the package is LDIDT, and so when the chip is transitioning from very quiet state to the very high power state, like running the lots of floating point unit instruction, then that DIDT is very high. So do you do some those DIDT control to suppress the fast like active current transition? And if you do, how do you do that without affecting the performance? Yeah, so what I was showing there, that one workload is actually a floating point workload that we run that has very intensive floating point to look for kind of our highest DIDT and the lowest F max. In our bulldozer chip, we actually have some mechanism built into the hardware that will prevent rapid floating point instructions initially. So we could actually gradually ramp up the supply, or gradually ramp up the workload. So we don't get an abrupt, turning on all the SIMD units inside the core simultaneously, for instance. We could prevent that. And there's some hardware mechanisms there to do that. Performance impact tends to be very minimal because most applications, if you look at how the floating point's used, if you have a little latency on the very beginning of that floating point burst of operation, it has very little impact on the overall performance of the application because those kind of applications tend to be more streaming where you have very efficient use of the floating point, then it stops. So if we just add a few more cycles in the very beginning, that's kind of negligible. I see. One more question. So at the beginning, you mentioned some credit-based, like thermal management scheme, digital-based. But you could also do those control by directly sensing the temperature either on die or off die and throttle it. How do you see the pros and cons of doing like actual temperature sensing versus this digital scheme? Yeah, so the temperature sensing is very effective. We do that also for overlimits. So we have kind of this final protection with the thermal diodes on the die, where we could actually shut things down, if we see it overheating, and for some reason, our algorithm isn't working correctly, it'll shut down and protect the chip. The problem with relying on the thermal diodes themselves is that the temperature is actually kind of slow already. We've already kind of hit that point where with the prediction method, we could actually predict what's going to happen ahead of time because we could see the power, and because of the latency, from the power event and the actual, thermal heating of the chip is pretty high. We can then do a lot of things like boost, and then shut the boost down before we actually have a temperature problem. Like we don't want to actually, let's say, do a boost and then have a temperature problem, then turn it off. We want to proactively turn it off so we don't go into that problem of shutting down the frequency too low. Because one of the problems you could get is where you're boosting, and if you're always shutting it down, then your average frequency could be lower than kind of, let's say, kind of a moderate frequency you could pick. That would be constant. Thanks. Yep.
Todd Besnick, Quantum. I appreciate you coming here and letting me know that all the analog circuit design I took at school is worth something in the future. I'm wondering about some of the timings. You're talking about we have some hysteresis in the actual power increase that we're going to see, or the heating that we're going to see. What kind of lengths of time are involved that you can hide, say, a boost?
Yeah.
Is that a millisecond?
It's in millisecond range, right. For the time constants for thermal is very slow compared to what we could go in and out of boost.
Okay. It seems to me it would be useful to provide the information about the power usage on the processor back out to the programmer. Has there been any thought about that?
Could be. I'm not really involved in that part, so I really can't comment on that aspect. But there could be. I'm more looking at the design aspects of this, not necessarily so much of the programming.
If you were to provide a part that had that ability, you might find researchers using it and AMD benefiting.
Absolutely, I could see that. And I think power-aware compiling is a very nice topic that where the compiler actually could tell you what your code did and estimated opportunities for this.
Cool. Where's the power getting break-even point?
Well, it's actually very fast. The break-even point on if you have like a 40% leakage kind of process, if that much, then the break-even point could be on the order of tens of nanoseconds. So it's very low. If you have a very low leakage process, like a mobile process, typically it could be much higher. Maybe hundreds, maybe 1,000 nanoseconds, kind of thing.
Thank you.
Okay.
Okay, cool chips, Tadao Nakamura. Do you have a good concrete example of a relationship between the rush current, side effects, and frequencies?
Yeah, if you look at my plot, I gave actually the voltage drop.
Yes.
I didn't give you the exact numbers for the inrush current. That's somewhat dependent on overall capacitance here, that you have for decoupling and everything, and how it affects the frequency. So I don't know if there's a definitive, rule of thumb. Everyone that would be universal. But if you typically what we try to do is when power gating is do no harm. We want to make sure the inrush current is below the natural transients that the application could run during like normal operation. So I use that as the limit. Okay, so if our highest DIDT from just running, let's say FPU intensive workload going in and out, that would be the limit for my inrush current. I want to do no more harm than that, because if I go much below that, you can't tell. Yeah.
Okay, thank you so much.
Okay.
So I hate to cut off the discussion, but unfortunately we're out of time for this talk. There will be a break later on. I'm sure Steve would be happy to answer any questions then. So let's go ahead and thank Steve one more time.
Thank you.
So our next talk is going to be given by Don Gardner from Intel Corporation. So Don has been at Intel since 1991, and he's now a principal engineer there. He received his PhD from here at Stanford and also holds a visiting faculty or visiting scholar position here. Don has been very productive, has done quite a bit of work, not only in some of the integrated magnetics that he'll be telling us about today, but also in some of the initial work on integrating copper onto CMOS. So rather than tell you the long list of awards and achievements that he has done, including actually Intel's highest technical award for the work that, again, he'll be telling us about today, I'll let him just go ahead and dive in and tell us some more about that. So go ahead, Don.
Thank you. Where's the pointers? Grab it from Steve.
Okay. Good morning, everyone. I'm glad that we're all able to make it on time today. I guess tutorials tend to bring people on time. I'd like to ask, before I start, what everybody's field of interest is or background is. It kind of helps me decide how to position this presentation. So I'd like to know how many people here are like material scientists or chemists?
I see 1. Okay. Well, and then how many electrical engineers? Okay, fair number. Physicists? Okay, 1. And then computer science? Okay, so and then what did I miss? Any journalists, I guess? Okay, well, that'll be interesting because this talk does have about half electrical engineering and about a third material science. So obviously, there's going to be some stuff here that people probably haven't seen before if you haven't done much material scientist, which is only one person. So I'm going to be talking today about fully integrated voltage converters for on-chip power conversion. My distinguished colleagues here are, oops, I can point this right way, are shown here. And I used to be part of the circuits research lab at Intel, and I'm now part of the future technology research that's part of Intel Labs. So the outline of my talk is shown here. The first part of my presentation is going to be discussing DC voltage converters, primarily buck converters. And then I'm going to be looking specifically at the inductors that one uses for buck converters, which make up a sort of the point of weakness for trying to make an on-chip voltage converter. And then I'm going to go into some material science, and so hopefully people will indulge and perhaps enjoy something that they may not have seen before. Particularly, I'm going to be looking at magnetic materials. And then the third part of my talk is going to be looking at inductors that are fabricated with these magnetic materials that are fully on-die inductors and what we were able to achieve. So to start out, we had a great presentation by Stefan this morning where he talked a lot about voltage regulators and power gating and trying to basically manage all of the power on chip and sleep states and so forth and so on. And basically, if you look at that and you look at previous, in fact, presentations here in the last couple of years from other people on how to manage power, you'll see as many as 256 cores, but they all continue to use voltage regulators that are on the PC board. So what that means is that you have a lot of wiring to deal with, a lot of residual inductance and capacitance to worry about that you have to contend with to switch on and off that voltage, or lower it, which means that there's long delays involved. Of course, as we all know, microprocessors and GPUs and so forth all like to switch very fast. Workloads change very fast. So there's not really a very good match between how fast you can change the voltage versus how fast the workloads and so forth change. So ultimately, what is going to be needed down the road, whether it's sooner or later, is going to be something where you have voltage regulators that are integrated on the die, on the package, and not on the PC board in order to reduce all that latency and reduce the losses involved, reduces the amount of wiring you need, and so forth. So to that end, what I'm going to be talking about is that. Shown here is a buck converter, basic circuit design. You saw some of the other examples of other voltage converters earlier. This is a two-phase version. Basically, it's very simple. You have the input voltage coming in at some higher voltage, which, for example, 3 volts. And then you have switches that switch it on and off through an inductor. And then you have a capacitor on the output to help smooth out things. And then your load is over here. Oftentimes, these days, you'll see multi-phase buck converters. I've drawn one here that's only 2-phase. And so now you have 2 inductors with a mutual coupling between those inductors to worry about. So the losses associated with this kind of circuit are from the transistors, the switching losses from the transistors, as well as losses from inductors. So the inductor loss is only one component of the total loss, but it does make up a substantial fraction, say about 1/3 of the losses, generally speaking. So on the right here is a breakdown of the losses from the inductor itself. Typically, there's a DC loss, which is substantial when you start talking about spiral inductors, because you have now long wires, or toroids. They have a lot of DC loss as well. And then you have an AC loss component that you worry about, which is related to frequency, duty cycle. And then you have another component which doesn't show up in air core inductors, but does show up when you start introducing things like magnetics, and that's the hysteretic losses. So what we propose doing is to introduce new materials, basically magnetic materials, new circuits, which basically a multi-phase voltage converter that switches at much higher frequencies than what's traditionally been done. And then basically a new kind of structure where we have multiple, basically transformer windings, which each one connected to its own circuit. And by combining these three components together, one is able to obtain very high current voltage converters with good efficiency that you would not be able to do if you used any one of those three components separately. So here's something that was an early work that we set out to do. The idea was that if you looked at voltage converters, they all tended to operate at about 1 megahertz, somewhere at 3 megahertz, somewhere at 700 kilohertz. And the problem with such low frequencies was that you needed large amounts of inductance and capacitance on the order of microhenries. So the result of this is that you were not able to integrate this on die because it's just too much inductance to integrate. So what we set out to do was to first see if we can create a switching voltage regulator that can operate at a much higher frequency than 3 megahertz. In this case, we did come up with one that worked. It switched between 100 and 480 megahertz, and with an 88% efficiency. And this was something that we published at 2 conferences in the year 2004. And this is a comparison of that voltage converter compared to what was available at the time. If you look at this plot, the years across the top, better step over here. And then we have the various parameters that we were looking at. Basically, the switching frequency is here. You can see between 0.5 megahertz and 3 megahertz was pretty typical in those days. And the result of that is that you had to have a inductance in microhenries between 1 microhenry and 15 microhenries. And also the capacitance was in microfarads. So what we were able to achieve by increasing the switching frequency to 233 megahertz in this case was reduce the inductor and capacitor size by a factor of 1,000. So this sort of enabled us to finally be able to perhaps do something completely on die. So then that led to some other projects, which eventually led to this particular design, where we actually had an integrated voltage regulator here on the package with a CPU. And in this case, we had an input voltage of 3 volts and an output voltage of between 0 and 1.6 volts. It's no longer on-off, gated, or 2 voltages that you step between. It's a full range of voltages that you can use to fine-tune your voltage, literally on the die. The switching frequency was between 10 and 100 megahertz, which is significantly higher than what the on-package voltage regulators are. And we were able to achieve constant currents of 50 amps. Peak currents is 75 amps for this particular prototype. Shown here is the results of this particular design. On the x-axis is the load current from 0 to 80 amps, and on the y-axis is the efficiency. Now, you'll probably remember that our earlier presenter had pointed out that one of the problems with buck converters, especially if you start going to multi-phase converters, this one is up to 16 phases, is that when you start to lower your load to very low currents, that your efficiency starts to drop off a lot. So one of the things that this particular design has, it has adaptive techniques that help boost efficiency back up by cutting back on various parameters. Details of that particular study are published in the APEC paper that was presented last year. So now we're going to switch into what you need to do in order to make inductors that can do some of this stuff. If you look at inductors that are basically done on die these days, what you'll see is, for example, this particular die, which was actually taken off of the cover for a book called RF CMOS Integrated Circuits by Tom Lee here at Stanford. So it's pretty representative of the, what's out there. You can actually figure out how much area is consumed by the inductors. It's on the order of 24% in this case. So one of the parameters that we started looking at is what is the inductance density? Because obviously you don't want inductors to take up a lot of area, not only because silicon chips are expensive, but because you have a lot of resistance associated with these long coils. So the inductance density is typically for air cores less than about 100 nanohenries per millimeter square. So this is a comparison of what was available up until recently in terms of inductance that are on die that use magnetic materials. And what I'm plotting here is the peak quality factor, which is dependent on frequency, versus the inductance density of different structures. Now, you have the planar spirals and elongated spirals. Remember, I mentioned that those have a lot of DC resistance. So those are not very good candidates for voltage converters if you have high currents. And then we had another type of inductor, which is called a strip line inductor, which rather than actually making a coil, it's just a straight inductor with magnetic material wrapped around it. Those are good candidates for DC voltage converters. And then we have toroids and meanders, which again have a fair amount of DC current. If you look at this graph carefully, one of the things you'll notice is that a peak quality factor of 1 or less means that the device is more resistive than inductive. So it means basically you're making a resistor with parasitic inductance. So anything that is sort of below this line is really not something you would want to use in anything serious. In a different way to look at this, the peak inductance density that you can get with air core is about 100 nanohenries per millimeter square, which I mentioned earlier. And you can see that most of these devices that use magnetic material, on the left here, actually are in that same range of what you can get with air core inductors. And indeed, you'll find that a lot of these particular designs, looks like my pointer died. I'll have to do the battery change. A lot of these designs actually only show about a 20 or 30% increase in inductance when they introduce the magnetic material. So that means that you're not going to be able to convince any fab or product designer to include the cost of the production costs of magnetic materials into your process if you're not going to be getting that much benefit from it. So that basically leaves the region over here where we were and some other researchers were, and that is we're getting something reasonably good for inductance density while maintaining a peak quality factor. But one of the things you can note from looking at this graph is that there does tend to be a trade-off that sort of follows a line such as drawn here, whereas if you push your inductance density to higher values, your peak quality factors tend to drop down. So that means that you need to try to balance the two and pick the best peak quality factor. For example, you might want something in this region over here, while you still have an inductance density that benefits from having the magnetic material. So now we're going to look a little bit at material science. So the one person in the audience will enjoy this part. Basically, this is a magnetic hysteresis loop for a magnetic material. What's plotted here is the applied field versus the flux density. And basically, with the amorphous cobalt alloy that we chose, we have a slope which corresponds to permeability of about 1050 in this case. Another material that's commonly used for inductors is a nickel iron permalloy, which has a higher permeability. What you'll notice on these things are a couple of key parameters. One is that the saturation point, which is important when you're starting to flow tens of amps, is a little lower for this particular material versus that one. So you might say, well, why don't you pick something that's even higher? Well, the best known in nature is around 2, a little over 2. So that means that you're not going to be able to push this number very high. So one of the trade-offs that happen is if you have a higher permeability, which means you have more inductance, it'll saturate sooner because it'll get there a lot faster. So you have to sort of trade off your permeability versus what kind of currents you're going to flow. The other parameter that's kind of important to pay attention to is if you remember in the loss components for the inductor, the third term was hysteretic losses. Well, that's what's happening right here. You have an opening here, and what happens is that you're going in one direction and then you switch in the other direction. There's a period of time where the permeability is something on the order of 1 or something smaller than the permeability of the device as it switches over from this side of the loop to this side of the loop. So you have these minor loops basically going on. And so that means that your inductor does not have as much inductance as you want it to, and then you end up having some losses. So this here is a plot of that permeability, which was the slope in the last line, versus the applied magnetic field. And one of the things that you can see here is when you have a higher field, the magnetic material will saturate. It'll tend to saturate from the inside out for something that wraps around the line. The other thing that shows up in these types of measurements is you'll see the permeability is actually dropping as you increase the thickness of the magnetic material. So you have to contend with that. So here's an equation that basically is the skin depth equation. For material scientists, this should be pretty easy to understand. The skin depth is related to frequency here, and it's related to the resistivity of the magnetic material. So that's key. You want to get that resistivity up so you don't have too bad of a skin depth. But another parameter that a lot of people don't realize, because normally when you look at skin depth, you're looking at conductors that are not magnetic, is it's dependent on the permeability of the material. So that means when you start dealing with magnetic material, the higher permeability, the worse your skin depth problem is going to be. So here's a plot of the skin depth versus frequency that was calculated, and then some points here that, for our devices. And you'll see that for switching frequencies of, say, 1 gigahertz, that the skin depth is on the order of half a micron, which is pretty typical for the types of dimensions that we're dealing with. So that means we do have to worry about this. Over here on the right is a model that takes into account the frequency through things like the imaginary component, the skin depth, the intrinsic permeability at DC, and then the thickness of the material. And you can actually model this fairly well with this particular equation, and it does allow you to then go back and look at what it is that your magnetic material can actually accomplish, such that you can then see if your inductors are behaving or if there's some problems with it. The nice thing about the amorphous cobalt alloy that we focused on was that it has a resistivity of about 100 microohm centimeters, which is relatively high compared to permalloy, which is about 20 microohm centimeters, and permalloy being the most common magnetic material that's used for inductors. So, okay, so here we're plotting permeability versus frequency. And on the left is the real component, the right is the imaginary component. The imaginary component comes into play when your B and H fields are 90 degrees out of phase, so you don't want that. Basically, it results in losses. What you see here is that depending on the film thickness, the roll-off and the permeability will start to kick in at lower and lower frequencies. Remember, we were trying to make our buck converters operate at above 1 megahertz. We want to push them up to hundreds of megahertz. Well, if you look here at 100 megahertz, you can see that roll-off starts to happen as you increase your magnetic film thickness. So that means that you're going to have trade-offs now. If you're going to saturate your magnetic material, then it's useless when you start dealing with tens of amps. So you have to pay attention to this. So that model that I showed in the last equation actually models this fairly well based on Maxwell's equations. You can actually see that what's happening here is exactly what the theory predicts. So that means that our magnetic materials are limited by what's called eddy currents. So now I'm going to switch a little bit more to electrical engineering. So one of the things that a lot of researchers have done in the past is they said, okay, well, let's just throw magnetic material on top. In this case, I'm drawing on the bottom. Let's say on top of our wires. It's simple. You don't have to worry too much about processing unless you want to package it. But then, well, since you're a researcher, you don't make products anyway. So then why don't we just do that and make an inductor? Well, it turns out if you go through the equations carefully, you'll find that if you have one layer of magnetic material, the biggest increase in inductance you can get is 2x. That's independent of the permeability of the material. So that means you can put a really high permeability material in there, but all it's going to do is get to 2x faster as a function of the film thickness. This is what happens when you have a magnetic material with a single wire. Now, one way you can get around this equation is by wrapping the wire around the magnetic material. But when you're talking about DC voltage converters, more wire means more DC resistance and more loss from the DC resistance. So that's not a very good way to go, especially when you're talking about, as I said, tens of amps. So the other way to go about it, which is unfortunately more expensive but works, is to wrap your wires in magnetic material. Now, in that case, you can actually get permeabilities or inductances that increase by the permeability, the relative permeability. So if your permeability is, say, 1,000, if you had magnetic material to infinity, your inductance could then have an increase of 1000x. Obviously, we're not going to make inductors that have magnetic material to infinity, so you have to basically live with something that's not 1000x. But you can get better inductance with magnetic material this way. So we set out to make some structures. Shown here is a spiral, another spiral with magnetic material that's actually patterned in stripes, which is to help reduce the eddy currents. And then the holy grail for voltage converters, and that is a stripe inductor, where we have a stripe here without magnetic material and one above it with magnetic material wrapped around it. Now, the spirals are actually elongated because the magnetic material has an easy and hard axis. Now, there's one direction where the permeability is a value such as 1000, and the other direction has a very high permeability but saturates very quickly. And what happens is when you apply a magnetic field during the deposition, which you do to try to reduce the coercivity, which is the hysteretic losses, what comes out of that is you end up having what they call a hard and easy axis, which is what a soft magnetic material is. So basically, there's one axis that has the good properties. So these structures are elongated to take advantage of that one axis. Here's a nice cross-section. This is a 130 nanometer metal process that was made at Intel. What you see here are 6 levels of your traditional copper interconnections. And then what we did is we took the wafer and introduced the magnetic material with the hard axes, as shown here, because the current is orthogonal to the picture, and then wrapped the inductor wires with magnetic material. You see there's multiple wires here. Each one could be one phase of a voltage converter. And then on the right here, you'll see what we call a magnetic via. Now, we call it a magnetic via because it doesn't have to have current going through it like a traditional via does. But you do want to get that magnetic flux to go around it. In fact, if you have current that goes around here, that's actually a bad thing. That means you're introducing more eddy currents. So ideally, you don't want to have too much current flowing in that part of the structure. So with this structure, we were able to, as I pointed out earlier, if you use a single layer of magnetic material, the most increase you can get is 2x. So what we did is introduce a single layer of magnetic material on some spirals. You can see that they're covering about 1/3 of the spiral inductor. And we're getting about a 10 to 30% increase in inductance. So that's pretty consistent with the 2x. That's the maximum we can get pretty much if you cover 1/3 of it, about 30x, or 30% increase. The nice thing that came out of this, though, is that we can make inductors that operate at well over 1 gigahertz. That was a first. People did not successfully make inductors that operate over 1 gigahertz. So you can see here that the increase in inductance is not that great on the smallest inductors, but you do get this 10 to 30% increase in inductance. And it's up to 9.8 gigahertz in the smallest inductor. So that really showed that, hey, we really could do something with magnetic material. So then what happens if you wrap it with 2 layers of magnetic material? Well, we got a 9x increase in inductance by doing that. And that was a first. If you looked at the literature prior to this, it was mostly on the orders of 20 or 30% increase, even with 2 layers of magnetic material. And that was largely in part because the magnetic vias are really key to getting this to work right, and it's a challenge. But unfortunately, these inductors don't work very well at much over about 30, 40 megahertz. They start to roll off. The inductance is dropping. What's going on there? Well, it's those eddy currents again. Remember, in the last slide, it went clear up to almost 10 gigahertz. In this one, it's dropped by a factor of 100 because of those eddy currents. So that really shows you that you have to deal with those eddy currents. You've got to figure out ways to deal with them. Increase the resistivity was one of the keys. And already we're using a cobalt alloy here, which is 5 times higher than the permalloy that most people, the most common magnetic material that would be used for inductors is. So here's a picture of another way that you can deal with those eddy currents and skin depth. Skin depth, I should point out, is similar to eddy currents. In fact, you can model them by little micro eddy currents. This is the magnetic flux density in the magnetic material at 1 gigahertz. And what you see is that when you go up to those high frequencies, that skin depth kicks in and all the magnetic flux gets pushed out to the surface. So one of the ways you can deal with that, which I'm sure you've all heard of laminated transformers, is to laminate your magnetic material. which is what we did here. You can see the laminations actually make the flux now stay fairly uniform throughout the magnetic material. So this led us to the next prototype, which was one that used a 5-micron thick copper layer. So now we're talking serious copper here that can now start to handle these kinds of currents that we want to be able to handle. Again, you have an elongated spiral inductor. Again, too much DC resistance for a serious voltage converter, but still something that can be used for perhaps RF circuits. And then the lower left and the lower right are stripe inductors wrapped with magnetic material and slotted magnetic material to try to deal with those eddy currents again. Shown here is a cross-section of that new structure. This was done in the 90 nanometer CMOS technology. And you can see the layers of copper underneath, and now you can see these seriously large wires compared to the other layers of interconnections with magnetic material wrapped around it. We have 4 wires here, and then we have a magnetic via. You'll notice this magnetic via looks rather different than the other one. It's a lot rounder corners. You can see the step coverage is better because of that, and therefore you have a much better coupling between the top and bottom layers of magnetic material. Very important. I still see researchers to this day make magnetic vias that don't even connect up the 2 layers of magnetic material. But you want that flux to wrap around. You don't want it to go off into space in order to maximize your inductance. So here's a blow-up of that. What you see here is a thin layer of dielectric. This is your sort of typical TIOS silicon dioxide layer. And then a polyimide layer that's deposited over the thick copper wire that was electroplated, and then the multi-layered amorphous cobalt alloy. The results of this were even better than that 9x increase. You can see here we got a 16x increase for the spiral inductor. In fact, the inductance was so much better, it was at 200 nanohenries, still not microhenries. Remember, the 1 megahertz inductors want microhenries, but it is 0.2 something microhenries. And in fact, this roll-off here is because of the RC time constant now. Now you've got capacitance from the wafer and so forth, and it's rolling off because of that, not because of eddy currents and other effects. It's not a materials issue, it's actually an electrical engineering issue that causes this roll-off. We've got so much inductance now that we have to contend with it as a circuit element. The inductance density, if you remember, for air cores on less than 100 nanohenries per millimeter square, probably more typically you see numbers on the order of 10 nanohenries per millimeter square. But with this device, we're getting 1,700 nanohenries per millimeter square, which comes from that 16x increase. For voltage converters, though, we want something that has low DC resistance. So that is what we would like to use, a stripe inductor. And shown here is the result of making stripe inductors with magnetic material. You can see the inductance increase is between 24 and 31 times increase. Still not, the permeability of the material, which is, 800 to 1,000, but that's because we don't have magnetic material infinity. But we are getting substantial numbers here now. This is serious enough that you could actually perhaps consider doing things on chip, on die. So one of the things that we found in the literature, which was really helpful for the work, was some work that was done by Corinne. I can't pronounce the name too well, but the inductance can be approximated by the permeability of the material, the thickness of the magnetic material, and the length over width of the structure. Now, that approximation goes away if your length and width are similar. There's, I think, a tangent term that comes in. But as long as your structure is much wider than is high, you can use this approximation. Or for the electrical engineers in the audience, which there are many of you of, you're probably familiar with this sheet resistance that a lot of times is measured for thin conductors. So basically, you're measuring ohms per square. Well, in a similar way, we can measure the inductance per square, or the henries per square. So if you plot 1 over the inductance versus the width of your structure, the total width, including the wires, whether there's gaps in the wires or not doesn't matter, because the current's going to be what's important. You can plot that if you have different width structures and then get the sheet inductance out of it. So now we can start to study how the planar part of the inductor behaves. Now you might wonder, well, why is that so important? That's because the magnetic vias are not part of that planar structure. The magnetic vias contribute what we call a shunt inductance. So 1 over the shunt inductance is where this intersect occurs. If the shunt inductance is near infinity, then this intersection will be at near 0, which is what you want in the ideal case. But it now allows us to study what's going on in the planar portion of the structure versus what's going on in the magnetic vias. So let's see if we can use that equation in some actual measurements and sort of extract what's going on. So now we're really getting into the nitties and the gritty of an inductor. And you're thinking, oh, this inductor is simple. It's like a capacitor, right? Well, I think you'll see here that there's a lot to it. So what I'm plotting here is inductance versus frequency for inductor structures where the only difference between the structures is the width of that magnetic via. And you'll see that that width is really important. If you have a magnetic via that's on the order of 4 microns, the inductance is way down here. As you increase that magnetic via, it quickly jumps up, and then it eventually saturates. So that flux is wrapping around from the top to the bottom layer, and the wider that via is, the better. But at some point, it doesn't really get much better. So we can use that equation from the last side and see if we can extract something if we have different widths of these structures. So this is one width, but I actually had multiple widths available to me, so we actually were able to measure these and extract the sheet inductance, so nanohenries per square versus frequency, and then the shunt inductance, so it's nanohenries per millimeter, so the longer inductor, it takes that into account. And then we were able to extract that, and lo and behold, depending on your width of your via, the sheet inductance is all pretty much similar. So that means that this really does separate the effects of the vias versus the planar part of the inductor. The simulation does show that the sheet inductance should be something on the order of 1.2 nanohenries per square, but gee, we're only getting 0.8 nanohenries per square. So we can look at this device and say, okay, we need to go and figure out what's going on in the planar part of the inductor. Well, one of the things that oftentimes happen when you're trying to develop a process such as the polyimide process is you'll get like this waviness because it's not completely planar. And that can actually drop the sheet inductance, which is what happened in this case. Now, if you look at the magnetic vias, what's plotted here is different width magnetic vias and their shunt inductance versus frequency. And what you see is that a 4 nanohenry via has a fairly low shunt inductance of less than 10 nanohenries, which is pretty darn low. And as you increase that magnetic via width, it can get up to values of around 30 nanohenries, which is getting pretty okay, but still not the greatest. But basically, if you do a simulation, for example, of an 8 micron via, shown here as a dotted line, compare it to the orange line, you can see that actually the magnetic via in this case isn't too bad. It's not that far off from simulation, except at higher frequency you start to have a larger gap there. And that's because the eddy currents are kicking in. So this basically allows us to look at our inductor structure and say, okay, in this particular case, we need to go look at the planar part of the inductor. And that's really important because so many times we would get some inductors and measure them, and the values weren't that great, and we're like trying to figure out, well, what happened? And everyone's saying, oh, well, it must be the magnetic vias. And I can't tell you how many times we discovered it wasn't. It was the planar part, or vice versa. We look at it, and hey, it doesn't look planar. It must be that. And when we looked at these measurements, oh, it's the magnetic via that's creating a problem. So this here is showing one of the things that shows up which causes that extra drop at the higher frequencies. And that is that here's your copper wire with the current that's flowing into it. On the top is the unlaminated case, and on the bottom is the laminated case of the current density. So now this isn't the field that I showed earlier. It's the actual current. So you see the wire has a lot of current, obviously. That's where you get like amps of current. And what you see is that there's a lot of eddy currents that flow on the bottom surface of the magnetic material. They get to the end of the inductor, they turn around and wrap and come back along the top of the magnetic material. So that's sort of what you would normally see in like a laminated transform or something. So the thinner you make your laminations, the better, because now the resistance that current has to go through is higher, because it's basically thinner magnetic materials. That's how lamination works. Well, with these structures, we have a disadvantage. We have this magnetic via. And what happens is you get a lot of current flowing in one of the two directions in the magnetic via. So now you have this sort of three-dimensional effect going on. So that in itself means that you really have to work on those magnetic vias and make them not allow too much eddy currents. And even when you laminate, you can see that you still end up having eddy currents in those magnetic vias. So if we want to see how well we can do this with laminations, this here is an analytical model that looks at the quality factor as a function of frequency. So now we're not looking just at the peak quality factor, we're actually looking at the quality factor for all frequency ranges. And what's plotted here is the quality factor for different thicknesses of magnetic material. So 0.125 microns thick, which is really thin, so that means your eddy currents are going to be less, versus 1.5 microns thick, which means you have more eddy currents, but you're going to have a lot more inductance because you have more magnetic material. If you remember from the models, off to infinity is best. But what happens is as you increase the thickness, your quality factor is dropping. In fact, it went from 20, which is pretty darn reasonable for any kind of converter, down to something on the order of only 5 or so. So that's not so good. So if you keep your eye on this thicker magnetic material, in this case 1.5 micron, it's this dot dash line. In the next slide, I'm going to replot this line as a solid line, and then I'm going to plot other lines that were calculated for the ideal case where the magnetic via just wraps around the magnetic material. I forgot to mention that. That's what this analytical model was doing. It doesn't look at that, what's going on in the actual via if you have these wing-like structures. So if we watch this slide as I switch, here's the solid line for the one lamination that's 1.5 microns thick. And as you increase the laminations from 1 to 5, you can see that your quality factor can be brought back up to a really decent value of over 20 at fairly high frequencies. So this is what we would like to ideally obtain. But as I pointed out 2 slides back, you have laminations in the magnetic via, and you still have eddy currents. So what can we actually accomplish? And that's what's plotted here. We have the quality factor as a function of frequency for different width stripe inductors with different numbers of laminations. And what you see is that as you increase the number of laminations, in this case from 4 to 8, 4 to 8, 4 to 8, you do get an increase in the quality factor at a slightly higher frequency, but that's not anywhere near what the analytical model is predicting. Well, if you look at this graph more carefully, at the low frequencies, you'll see maybe an explanation for that. And what you see is that basically the quality factor drops for, like in this case, at 1 for 1 megahertz down to less than, or 0.4. And what that basically tells you is there's something dropping. Basically, the inductance is dropping. And that's because you have laminations now in the magnetic via, and that creates like gaps. So now the magnetic flux cannot wrap around it so easily. So basically, what this tells you is that you can only do so much lamination before your increase is basically diminished to something that's not worth doing. So in summary, basically, I showed you voltage converters that can switch at much higher frequencies than what's done on a PC board. We're looking at up to 480 megahertz in one of the papers that I showed. In order to do that, you do need things with high inductance density if you want to do it fully integrated on die. The DC resistance is very important for all of these structures. Some of the papers I showed earlier don't have on-die voltage or inductors, I should point out. But what we did do was increase the frequency to see if we can do something at high frequencies. So you need to look at those papers that way. And then magnetic materials, we looked at the complex permeability, the real and the imaginary part, which creates the losses. Hysteresis is very important. And then a whole area that I didn't touch on at all, but if there were more material scientists, I have probably another 15 slides I could show you, that it really needs to be CMOS compatible. You can't just throw something on there and expect it to stick and be able to pattern it, be able to make the oxides in the lamination, have the deposition process be reasonable, be able to deposit dielectrics over it, have the dielectric stick, and pattern that as well. There's a lot of issues. Thermal is another issue. Not only thermal during depositions, but thermal when you're using it. Does that affect the magnetic properties or not? We've had cases where the deposition process for putting down the dielectric was supposedly never reached temperatures above a couple hundred degrees, and it turned out that it was not cooled in one particular part of the process that caused the temperatures to go high enough that it actually caused the magnetic material to fail. And nobody could figure out why, because the people who knew that tool were certain that it never went over those temperatures, but sure enough it did. And then I showed you inductors that use magnetic materials. With a single film, we got inductance increases by up to 30% for the spirals that were 1/3 covered, up to really decent frequencies. Magnetic vias are a key part in getting these kinds of inductances. And one of the things that we did to study these was the sheet versus shunt inductance. And we were able to get over 30x increase in inductance when you use 2 magnetic layers, and we can even create 200 nanohenry inductors. So with that, thank you, and take questions.
Hi, I have a question about, kind of overwhelmed about the materials aspect of this, which is pretty impressive, but I was going to ask you about the practical application of it. So one of the things that's obviously very important is the high frequency of response when adjusting voltage on the chip. But I wanted to ask you a little bit about the efficiencies of these voltage converters relative to the off-chip ones. What is the rough efficiency of the voltage converters? How much power losses are in those compared to the?
So let's see here. I can go back to the beginning here, I think. Get this to work. Here we go. So shown here is some efficiency measurements of voltage converters. Now this one has 2 kinds of inductors. One is a discrete powdered iron core inductor, and then the other one's an embedded air core inductor. And so there's efficiency numbers here of 85 roughly to 88% if you use the discrete inductors.
How does that compare to the off-chip?
Well,
I mean, it's pretty good, I guess, so it doesn't matter too much.
Yeah. I'd have to think back at the papers that were published, but the numbers were in that same ballpark, but that's pretty much all that's been published, so I can't really speak to much beyond that.
Okay, thanks.
Yes?
About the package integrated the voltage regulator, does that have the advantage of achieving the faster the regulator turn on, turn off time, and hence reduce the need of the on-die power gating, which first speaker talked?
Absolutely, that's what you want, is to reduce. I mean, you can think about this. There's so much work looking at C states and power gating and all that, because basically the voltage regulators are on the board, and it takes milliseconds for that voltage to change. So most of the time, your loads change so fast that you can't take advantage of that. So by having the voltage regulators more integrated, now you can switch that core or multiple cores to the optimal voltage much more quickly. And in fact, you can have perhaps one core at a high voltage that's operating in turbo mode, and the other cores can be at a lower voltage, but still doing calculations, like doing stuff with the internet or whatever like that. And then you can also think of the uncore. I should mention that we actually do have a 48-core prototype. That's the single chip cloud computer, SCC for the abbreviation. The marketing people named it that. That we've actually put together as a prototype and distributed to about 100 universities nationwide that actually has 8 voltage converters on it. And each voltage converter will handle, I think, 8 cores, and then the uncore will have its own voltage converter. So with that, you can dynamically change the voltage. So what we did is we distributed these systems to researchers that are dealing with parallel programming applications and so forth, to try to see if they can start to create this whole new way of looking at power delivery, where you actually can dynamically change the voltage to what you need for banks of cores or individual cores, as opposed to having to deal with, like you said, power gating and sleep states. Because it's rather different when you can actually adjust the voltage at a fine-grained level.
Okay, one more short question. So for the on-die, those inductance, does that interfere the chip operation, causing those inductive noise?
Well, I can't give you any actual numbers, but the nice thing about this versus, say, not using magnetics is that the magnetics actually confines all the magnetic field to that region. So now you actually have less of a problem than if you were to try to do it like an air core, which really would be like dielectric and silicon core version, where the fields actually extend out into the substrates and you end up having eddy currents flowing in the substrate itself. But if you wrap it with magnetic material, it's like shielding. So it really actually helps. But remember, when you have a stripe inductor, it's more, not as concentrated as you might think. It's a few nanohenries as opposed to hundreds of nanohenries. And if you don't have the magnetic material there, now you're talking picohenries, and it's no different than, say, a wire that's going across the chip to distribute the power.
Thank you.
Hi, one basic question. Your slides, because they're all white text, they've not come through on the slides yet. Will an electronic
Oh yeah, I
copy
saw
be
that.
available?
That's a problem with, I think, everybody's hard copy. But there is a memory stick version that has the full color copies on it that you can look at.
Second question, obviously you're focused heavily on power supplies on chip. I mean, this looks so revolutionary. Is this going to make it to standard POL power supplies anytime soon?
Well, like I said, we do have that prototype out there already. We have the 48-core platform that's not a product, I should mention, but it is something out there for research. And you know, to me, it just seems like it's got to happen, whether it's next year or 10 years from now or further. Having the on-chip voltage converters is just, it's the next
So this does mean we're going to have a 12-volt going straight into the CPU?
What's that?
Does this mean we're going to have 12 volts going straight into the CPU?
Well, that would be the best way, because then you can basically reduce the number of bumps you need, because the current drops as you increase the voltage. Right. But you have to deal with the transistors being able to handle those kind of voltages. Right. And the transistors that you make microprocessors out of are usually only 1.5 volt transistors. So you have to deal with that problem.
Okay, thanks.
Hi, this is probably naive with respect to the magnetic material processing, but when you have some number of layers, 4 or 8 laminations, are you laying down the magnetic material, then some intervening material, then another layer of the magnetic material? And sort of secondarily, is each layer itself, would it be considered sort of a processing step from the standpoint of the silicon manufacturing?
That's a very good question. And the way we deal with that is that, I mean, if you did a process with a sort of just like permalloy or some magnetic material, you need to come up with some sort of good insulator between each of those magnetic layers. And even beyond your question, you have to be able to pattern it. You can't just like deposit it. So now you can imagine that this can get really complicated if you have to make, as you said, 4 or 8 laminations. So what we did to get around that problem was we took the amorphous cobalt alloy and we actually oxidized it. So it forms its own insulator. So by using an oxygen plasma, we formed a cobalt oxide of about, I think, 60 or so angstrom, and then we put the next layer of magnetic material. Now, not only is it all done in the same system, I mean, it could be a cluster tool or it could be the same module if you want, but you can also now etch it with the same etch process. So that's how we dealt with that problem.
Just a quick question about the sheet inductance on your slide. Just wondering if you have taken into account the skin effect in those like thick copper wires, and would that actually, if you try to like use like a lot more like copper wires, thinner ones, and would that kind of improve the sheet inductance in those cases?
Okay, the sheet inductance, oops, they took my slides away. The sheet inductance has to do with the planar part of the inductor. Mm-hmm. And what you're asking is if the skin effect in the copper wires affects the sheet inductance.
Right, because I think you mentioned it's like 4 thick wires there, right? I mean, that's...
Yeah, and I'd have to go back and look at the models to see what frequency the skin depth kicks in for copper at those thicknesses. But I do believe it does start to kick in, and it could be part of what's happening with the roll-off, is the skin depth in the copper wires as well as the skin depth in the magnetic material. Fortunately, today we have simulators that can simulate all that. 10 years ago, we didn't. In fact, there was a time where they actually took out the ability to model magnetic materials, and we were screaming at them. We were like, hey, how can you take this out? We need it, we're using it. And so then they put it back in the next generation. But now there's actually 3 3 or 4 companies that have pretty good simulators for inductors with magnetic materials. And I'm saying that in the past, you could just put in a constant value for the permeability. Now you can put in nonlinear BH loops. You can try to model the saturation effects. Where it's not yet is you can't model both things like saturation and hysteretic losses and everything all at once. But you can at least model one direction, and then you can model another, and then another, and get an idea of what each effect has and decide what to work on. So.
Thanks.
Satoshi Patsushita, NEC. My question is regarding the new materials. With the new material, the cobalt something, and then the quality factor is improved, I think that improves the efficiency of regulators itself, and also to make it smaller DC converter. Then how much the improvement do you estimate?
For the efficiency?
Efficiency and the size of the regulator. And then regarding the size of the regulator, if we can make it smaller, then we can control the smaller region of the unit instead of the whole chip or whole core or something.
Yeah, I can't give you any specific numbers because there's so many variations of the devices and the voltage converters and all that. And the losses are not just from the inductor. I mean, I focused on the inductor and its losses, but as I said, there's also switching losses in the transistors and so forth. But one of the benefits that you can get right away is that if you do use magnetic material, the inductors get smaller, the distribution of all of the current becomes shorter, and therefore your DC resistance will become significantly lower. I mean, if you got a 30x increase in inductance, you can imagine that everything will be 30x more or less smaller. So then that really helps with the DC resistance. So, yeah.
So how much is the reduction of the size of a regulator, total size of the regulator?
Well, I mean, it depends on the circuit design. If you want a 1 nanohenry or a 5 nanohenry inductor, and you've got a 30x increase in inductance, then it's basically 30 times smaller inductor. So, okay. But there's trade-offs involved again. Mm-hmm. If you want something that handles higher current, you have to deal with perhaps less of an increase in inductance.
Okay, thank you.
Yeah.
So I'll just ask actually one final question, which is following up on some of the previous ones. And perhaps this is too early to answer, so feel free to say so if that's the case. But do you have an estimate of sort of how much cost this additional material integration, et cetera, would add to a sort of standard baseline CMOS process?
That's a really tough question to answer because it depends on how many wafers you're making and how much capital equipment you have to buy.
Right, so let's assume you're wildly successful and this becomes part of the standard CMOS. So that's
yeah. I mean, we've done some cost analysis, and regrettably, I really can't discuss that because that does deal with products and business. But it is possible to model it basically. So yeah.
Got it. Okay. Thank you very much. So let's thank Don one more time for the great talk. All right, so I'm going to go ahead and get started. So this is going to be the third and final talk of the day, and obviously be presented by myself. As Kirste mentioned earlier, I'm on the faculty at UC Berkeley, and this work that I'll be presenting, which is on fully integrated switched-capacitor, DC to DC conversion, is done with my student, Han-Fook Lee, as well as Professor Seth Sanders, my colleague. And hopefully the slides will come up here shortly. There we go. Okay, so I'm fairly confident that in this audience I don't have to spend too much time discussing why it is that we would like to actually have integrated voltage converters onto the die. I think that was actually covered very, very well by the first two presentations. But I do usually like to start this out by just sort of pointing out something that's somewhat, let's say, interesting or ironic in some senses, which is that it's very clear that multi-core chips are here. This is really very much the standard these days. But however, in terms of really doing multi-supply chips, that's really not gotten to the same level of really adoption. And that's kind of surprising in that it's pretty clear that you'd really like to have many different supply voltages once you've gone to something like these multi-core chips. Because as was discussed earlier, you'd like to be able to, for example, run one core at its maximum throughput, for example, have another one simply dealing with some background tasks and so on and so forth. You could do it for things of that nature or perhaps even just to compensate issues such as variability. But I would really argue that if you look at where things are today, true multi-supply adoption really has not happened. Now, you could argue that power gating is some, let's say, subset of this, because there are indeed sort of local separate rails for each individual core or section of logic. But really, this is not sort of the vision that has been talked about so far, particularly this morning, but really in terms of being able to use these different voltages in each and every single core or perhaps even functional unit. So the perhaps obvious question to ask is, well, why don't people just take multiple external DC to DC converters? So for example, if you had 100 cores, just use 100 external DC to DC converters and bring all those supplies into the chip to get you that functionality. So I think Steve actually did a really good job explaining sort of some of the issues related to why that's very, very difficult to do, and I'll follow up on that in one more slide. But I should also mention that simply from a system cost and integration standpoint, very few people really want to deal with building 100 external converters or really paying for all those components, populating them, and then obviously dealing with all the mess you get trying to get those supplies onto the chip. But even if you sort of ignore that issue, there's a very big, let's say, practical issue, which is that if you think about especially the very high performance space, where at the very high end, these parts are typically operating about 100 watts or so. Now, you should keep in mind that 100 watts is actually done at 1 volt, which implies that you need 100 amps of current flowing into the part. So if you just kind of run the quick back-of-the-envelope calculation as to what the impedance you need through that entire power distribution network in order to ensure, for example, just a 10% voltage drop, so in other words, 100 millivolts, that basically means you need something on the order of a single milliohm of resistance in that entire distribution network, okay? That's a really tough thing to do. I don't know how many of you guys have seen like 100 amp cables, but these are pretty hefty, substantial things, and you can really see them. And so that's the kind of impedance levels we're talking about here. So the very sort of long story short is that the other reason why you really can't just take a bunch of external converters and use them to generate all these voltages is that basically that would force you to split the package power planes into all these smaller little domains. And basically, as soon as you do that, you really have a very bad impedance issue. So there's lots of different ways of thinking about them. Again, I think Steve actually did a very nice job sort of explaining some of those issues. But just as another sort of look at it, what you're really doing is once you've split the planes like that, essentially you really have to rely only on your own local resources. So you really don't get to rely on the fact that, for example, it's highly unlikely that everything on the chip will all be doing sort of its worst case activity all at once. Whereas once you've partitioned, now you're really just dealing with your own particular core, for example, and indeed that may have worst case on a fairly regular basis. So in case you don't sort of believe me or Steve for that matter, if you just sort of look at many of the typical high performance chips that are out there, you'll still see that the IOs are placed on the edges of the die, even though you have flip chip technology, which if you thought about it, in a naive standpoint, would have said that you can kind of put the IOs anywhere you want. You put the IOs on the edges because you still want, basically in the package, a nice clean slug of power, both in terms of the plane and in terms of all the vias going into the chip itself, okay? So what this basically says is that if we really want to get these local voltages onto the chip and be able to tune them independently, we basically have to do some form of on-die voltage conversion, okay? So just generically, if I take it so that indeed each power domain that I have has its own local DC to DC converter, then what I've enabled is now I can still have this single global low impedance input, but indeed I can locally generate these different supply voltages, okay? Of course, the key challenge in doing this is, well, how the heck do you build this fully integrated DC to DC converter? And I don't think there's too many people in the power electronics field here, but just because this is often sort of a misconception that's used in that area, when I say fully integrated, I really mean fully integrated. So energy storage, transistors, everything has to really be on the chip. Because any time you sort of start playing with these other games, you very quickly end up paying either substantial area, cost, or efficiency penalties, okay? And so that's why, again, I think you heard earlier from Don, there's a lot of interest now in these integrated magnetics to really get that key energy storage element onto the chip as well. So just to sort of, again, make sure that everyone is on the same page, there's kind of two rough, broad categories that you can think of in terms of doing switching DC to DC converters. And you'd really like to do these switching DC to DC converters so that essentially the efficiency you get can be high even with a wide voltage range at the output. So by far the most common type of converter that exists today is the so-called inductor-based buck converter. So that's this sort of simple circuit that's shown here. And in case you haven't seen them before, the very basic idea is that these two switches here, you can almost think of it just like an inverter. But what you're really doing is changing what percentage of the time that inverter is outputting essentially the input supply, and what percentage it's outputting ground. And the idea is that you're basically creating this square wave kind of waveform, which just goes through this LC filter to essentially get the DC value at the output. Now, what's nice about this is that it's pretty easy to change that DC value by just changing that duty cycle of that inverter at the input, okay? And so because of this simplicity and the fact that indeed you can get pretty high quality inductors in off-chip applications, this is really kind of the most dominant converter that you'll see these days. There is, in fact, however, another potential option, and that's the so-called switch capacitor type of topology. So the idea with switch capacitors is that basically you connect a capacitor, for example, either between the input voltage and the output voltage, and then in the next clock phase between the output voltage and ground. And by doing this, you can basically set it up so that there's effectively a division of the input voltage based upon how you configured that capacitor. Now, if this doesn't make immediate sense to you, don't worry. I'm going to say in a lot more detail how these things really work. But the key sort of point here is that now, rather than just changing something like the duty cycle to get you a different voltage at the output, now to get a different voltage, you really have to change essentially how you've connected that capacitor in the different phases. In other words, the topology of the circuit really then sets the conversion ratio that you get, okay? And so as you can imagine, if you want more and more control of that conversion ratio, that requires you to have more and more components in this circuit design. So actually, largely because of that region of needing more and more components, the switch capacitor topology has a lot of perceived disadvantages. So again, you don't see too many of these in off-chip applications. The inductor-based buck is really much more popular. Having said that, as you noticed from the title of my talk, I said I was going to be talking about switch capacitors. So you may be wondering, well, OK, so why am I going to be focusing so much on switch capacitors here? So the real key motivation here is that what's great about switch capacitors is that essentially I can do these in completely standard CMOS technologies, right? Because basically, if you think about just a transistor, it's got a nice thin oxide. I can build it very, very densely. That essentially gives me a very, very high quality capacitor with extremely high energy storage density, okay? So in other words, what I'm really going after here is trying to figure out what is the lowest cost way we can actually integrate these voltage converters onto the chip, okay? Now, this is by no means to say that developing on-die magnetics is not useful. In fact, if we were to able to get that into sort of the standard mainstream flow and do that in a low-cost way, there's many, many ways you can utilize those inductors in something that looks like these switch capacitor topologies as well. So again, that's not to say that magnetics are not useful. This is only to say that what we're focusing here on is really the low-cost aspect. And as soon as other technologies become available, we're more than happy to utilize those as well. The other thing that's an important point to mention is that many of the perceived disadvantages in the PCB world were, again, having to do with the fact that you needed a lot of different components. Well, if you think about it in the integrated context, the number of components is not what matters, right? It's the area that matters. It's the design complexity that matters. So as long as I can come up with things that are fairly easy for me to, in some senses, partition, which indeed capacitors work very well from that standpoint, then really that's not such a big issue to be dealing with. So really the biggest question then is, if I indeed am sticking to a standard CMOS process, so in other words, I'm not going to be adding any additional steps or anything like that, the biggest question is essentially going to be, first, of course, how efficient can you make these converters? And second, how much area is it going to cost you to build that converter to supply power to the entire chip or to sections of the chip? And as you can imagine, there's always going to be a trade-off between these. In other words, if I'm willing to spend more area on the converter, I can make the efficiency higher than if I force the converter to fit within a smaller area and supply the same power at the output. So in other words, what you really care about is the power density delivered by that converter. So many people have actually noticed the fact that indeed capacitors, they're widely available. They have essentially high quality factors. And so there's actually been reasonable amount of work beforehand really looking at these switch capacitor converters or fully integrated switch capacitor converters. So I've just selected a couple of representative designs here. And kind of the main point to highlight here is that there have been designs that have achieved pretty reasonable efficiency, so over this sort of 80% or so, but at extremely low power densities. So just in case this number isn't clear, this is something like 2 milliwatts per millimeter squared. So for most applications, that would basically mean the converter would have to be huge compared to the actual circuit you're trying to supply. On the other hand, there's actually been designs that have demonstrated extremely high power density. So in this over a watt per millimeter squared kind of number. But unfortunately, the efficiency was sort of left something to be desired from that standpoint. So as I said before, what we really want to do is answer, well, what's the best we can do? So are these sort of trade-offs, or these numbers really the fundamental limits, or can we potentially really optimize these converters more heavily and end up with a better overall result? So in order to do that, what we really have to do is just, first of all, understand how the converter works. Second, understand that in the context of a digital system, because we'll see that has some implications on how you want to build the converter. And then finally, of course, really do that design optimization and see where it gets us in terms of the achievable performance and power density. So first, let's just make sure everyone's on the same page or has a basic idea of how these switch capacitor converters work. And usually the simplest way to do that is to look at this simplest of switch capacitor converters, which is the 2-to-1 step down, okay? So essentially, the way this thing works is that in the first phase, you connect this capacitor in series between the input voltage and the output voltage, okay? Now, of course, when I do that, anytime I have current flowing through a capacitor, the voltage has to change, right? So if you sort of look at this waveform out here, basically because I have current flowing in this direction, if I look at that output voltage, it's essentially ramping down over time, okay? Now, I should mention one thing, which is I've simplified this picture somewhat. I'm assuming there's no capacitance whatsoever at that output there. I'll explain why I did that a little bit later, but bear with me for now, okay? So basically, as I'm pulling current out of that capacitor, if I look at the voltage across the capacitor, I'm actually ramping it up. In other words, I'm sort of storing charge in that capacitor. So then when I move to the second phase, which is now where I put this capacitor in parallel, basically from the output to ground, then you can kind of see as soon as I make that switch, the output voltage is going to jump up, because it will essentially just go to whatever voltage was stored on that capacitor. And then again, it'll start ramping down, because I'm basically pulling charge off of the capacitor there. Now, if you sort of think about this a little bit, what's basically happening is that during this half of the cycle, I've directly taken half of the current that I needed at the output from the input. In the second half of the cycle, that's when I deliver the rest of the current to the output. And so if you sort of think about it, that's really where this voltage conversion is happening, right? I have half the current at the input, but double the voltage. So of course, ideally speaking, I haven't lost anything from a power consumption standpoint. So again, what you can kind of see here is that in this particular case, I got this 2-to-1 step down because of the way I was connecting the capacitors either in series or in parallel with the input or the output. So again, the conversion ratio or the input to output voltage I get is really directly set by the topology. Now, I should mention you could use the same idea to do a step up conversion. Basically, you just have to switch what's the input and what's the output. And this is true of most DC to DC converters. OK, so now that we have at least a basic idea of how these things work, the next thing we, of course, have to look at is what are going to be the loss mechanisms, or what are going to be the things that cause us to not have perfect efficiency. So the first one, which is actually somewhat different than the inductor-based buck converter, is that because you're basically flowing charge through a capacitor, if you really want to have a stable output voltage, there's effectively an intrinsic loss associated with that voltage drop you get across the capacitor, okay? So I'll explain, the more detailed mechanisms to why that happens in 1 second. But basically, that intrinsic loss is really sort of set by the characteristics of the capacitor and essentially how fast you switch the converter. The other one is essentially all of the parasitics. So obviously, the switches themselves, they have some parasitic capacitance. They have some parasitic resistance. In fact, the capacitor is never perfect. It always has some parasitics that you basically end up switching and just dissipating power on without really delivering power to the output, okay? So let's take a look at each of these loss components in a little bit more detail to, again, figure out what's kind of the best that we can possibly do. The most interesting one to really think about, especially in the context of digital circuits, is how does this sort of quote-unquote intrinsic loss come into the picture? And by the way, I'm going to be deriving this in kind of a different way than what most power electronics people do, but I think it'll maybe be more intuitive, particularly for this audience. So the first thing to keep in mind is that if you're in a digital system, at least in any synchronous digital system, then essentially your gate delay, of course, depends on the VDD. But it doesn't just depend on the average VDD. Really, in most cases, your performance is essentially set by whatever the minimum voltage you get is, okay? So if you think about those triangular waveforms that I was showing before, what that basically says is that you have to essentially count your performance as coming from only that minimum voltage. So in other words, at these times where I've gotten the extra voltage, unless I'm doing something much more clever, really I don't get any extra performance benefit out of it, okay? So you can think of that as essentially being something like an output resistance or a loss term. So that loss term is essentially basically set by, as I mentioned before, how big the capacitor is, how fast you switch it, and then there's some constant factor here that's just related to essentially the topology of the converter, okay? This is a very standard sort of formula for what a switched capacitor resistor would look like. There is, however, one more thing that you have to keep in mind, which is that even though I'm not really getting any extra performance, the load circuitry underneath doesn't really know that, right? So if I am charging and discharging all my caps inside of the circuitry with higher voltage, then guess what? They're going to burn more current than they would have otherwise. So it turns out there's actually an extra factor of loss just due to the fact that your output voltage has ripple on it, okay? So if you actually include that, in other words, you say, well, how much power is my chip burning versus what it could have burned if I really just had a perfect voltage exactly at that minimum value, then it turns out you actually have to double the losses that you would have otherwise accounted for. Okay, so that's kind of bad news because especially in this integrated context where it's all about how small can you make that converter to fit it into the rest of the chip, you're basically doubling the loss that you get from something that's already pretty much your dominant loss term. The good news, however, is that it's actually fairly straightforward to fix that problem, okay? And the simple way you fix that is actually very similar to what people have done in the buck converter world, where essentially what you do is you take the total capacitance you would have had before, and you split it into smaller pieces, and then you just drive each of those pieces on essentially slightly phase-shifted versions of the same clock, okay? In other words, you essentially interleave the converter. Now again, remember, in an integrated design, this really doesn't cost me anything because I needed a big capacitor there anyways. Chopping it up into smaller pieces really doesn't change anything from the overall area picture. So what's really nice about this is that it doesn't actually change anything about what that minimum voltage is, because if you sort of think about it, I still have the same net amount of capacitance and the same net amount of charge flowing out of it. The only thing I do is just reduce this ripple at the output, okay? So in other words, if I interleave my converter sufficiently, and typically something like 10 to 16 way interleaving is good enough to do this, then basically I'll get rid of that extra factor of 2 loss penalty that I was quoting earlier, okay? So again, that's good news because, you know, okay, I went from factor of 2 to factor of 1, but remember, this term is actually a pretty big chunk of the total losses in my converter. Okay, so now that we've understood sort of where this so-called intrinsic loss comes from, then now we can really start thinking about doing an efficiency optimization. So it turns out the key to doing an efficiency optimization in pretty much all of the converters is basically this trade-off between the so-called intrinsic losses, or really the losses associated with your energy storage elements, versus the switching or parasitic losses, okay? So the basic idea is that for these intrinsic losses, basically if you store more energy, or in our case, you have a larger capacitance per unit area, then you'll have lower loss there. Or equivalently, if you increase the switching frequency, then again, you basically have to store less energy per unit operation, and those losses will go down, okay? On the other hand, however, if you think about the switches, of course, if I have better technology, things will just get better there. But if I increase the switching frequency, then all of those losses will go up, right? Because if you just think about the CV²F, it's the exact same thing for the switches. Indeed, if you switch faster, then the switch losses will go up. So in other words, if you're doing an optimization of the overall efficiency, what you really need to think about is how do you balance out essentially the losses from the intrinsic components, which would tend to push you to a higher switching frequency, with the losses from those essentially switch or parasitic terms, which tend to push you towards a lower frequency, okay? And I didn't describe it too explicitly, but you can imagine sort of the same thing happens with choosing the widths of those power switches, right? You make the width wider, you'll have lower resistance, but you'll have higher CV²F losses. So if we just look in a little bit more detail at each one of those components, I don't expect that you'll walk through any of these equations, although to be honest, none of them is very complicated. Basically, again, what you can kind of see that I've highlighted here is in terms of this intrinsic loss, you'd like to make the frequency higher in order to reduce it. Whereas for all of these other terms, basically you'd like to make the switching frequency lower in order to reduce those losses. So for any given, let's say, size of converter and load current at the output, you can always figure out what is that best switching frequency and similarly best switch size to use to get the highest overall efficiency or the lowest overall loss, okay? So that's actually some fairly simple math that we went ahead and did. And I'm not going to, again, bore you with the details of exactly how you come up with these expressions. But it is actually useful to take a look at what some of the results are. So just to make life a little bit easier in terms of coming up with the answers, what I first want to do is just basically ignore one of the loss terms. And the first loss term that I'm going to ignore is basically the so-called bottom plate or parasitic capacitance associated with the main capacitor itself. And the only reason I'm doing that for now is just to sort of point out what one of the limits will be in terms of the achievable efficiency of the converter. Okay? So if we do that, you get this expression that sort of shows up here. I'll sort of point out a couple things about that expression in one more second. But the first thing to kind of notice is that actually, notice all these efficiency numbers are pretty high. And in fact, they're not with any sort of thing too exotic in terms of the capacitance densities. So even with something like a couple femtofarads per micron squared and something on the order of about this Siemens per millimeter squared, which is about equivalent to a watt per millimeter squared, we're still in the sort of over 80-ish% efficiency range. Okay? So the reason I went through this whole exercise of deriving that essentially expression was that it really does sort of highlight a couple of things. The first is that you'll notice what's really setting your efficiency here is essentially the ratio of something like V squared of the switches times the R on of the switches times the capacitance of the switches. For those of you who are into these things, this is something like the FT or the intrinsic speed of the devices relative to what's the output voltage squared, the load resistance, times the total capacitance you have in the converter. Okay? So in other words, what this is basically saying is that the smaller you make this RL, the higher the losses are going to be. So that actually explains why I mentioned the conductance density earlier, because it's usually easier to think of things in terms of that conductance density, meaning that if you make the sort of total area of the circuits that you're delivering power to larger, that tends to mean that the power they'll be dissipating will also be larger. So in other words, you can think of that as just increasing how much conductance the converter itself has to deliver. Okay? But if that's a little bit confusing to you, don't worry, just think of this as being the power density the converter is delivering. Okay? So again, if you look at these numbers, what's kind of interesting about this is that if you look at where these numbers are lying, if I can do about this watt per millimeter squared kind of number, that's about the same power density or conductance density as what a high-performance processor is doing. And in fact, that's actually about a factor of 10 higher conductance density than what most of your typical mobile or let's say energy-efficient parts are doing. Okay? But really the most important point here is just that, as you can tell, what efficiency I can get really trades off with how much area you're willing to spend on that converter. The more area you're willing to spend, the higher the efficiency will be. Okay? Now, there is one sort of important side note that I like to make here, which is somewhat unique to these switch capacitor converters, which is that, as we heard quite a bit earlier on, you very typically need explicit decoupling capacitance on your chip just to make sure that your supply has sufficiently low voltage ripple on it. Okay? Now, what's very nice about these switch capacitor topologies is that basically, for all intents and purposes, I'm really just using the same capacitors as perhaps would have existed in any case for those decoupling capacitors. Okay? So in other words, functionally, they basically play the same role. So if, for example, I could actually fit my converter into the area you would have anyways used for that decoupling capacitance, which is kind of conceptually what I've shown here, then indeed I can actually get this thing to be fully integrated with nearly zero additional cost to overhead. Okay? Now, this does say that if you want to be able to meet that constraint, that factor of 10 I mentioned earlier between essentially how much power density you have to deliver in the converter versus how much the chip itself is about what you're required to do. In other words, usually the decap area is something like about 10% of the whole chip area. So if I want to fit my converter into that, then basically I need to deliver 10 times as much power density in the converter as I do in the actual load circuitry themselves. So now I will sort of come back and reintroduce that loss term that I ignored. Remember, I ignored that sort of bottom plate parasitic loss term. You can indeed do the math and add that back in and at least get some approximate results. So now I'm actually doing that with some, let's say, reasonable, let's say, assumptions about what the capacitor technology looks like. But there's really sort of one critical thing that I want to point out with this, which is once I add that parasitic bottom plate term in, you'll notice that there's essentially, the loss is not just something directly related to the power density, but it has this kind of fixed term sitting in front of it. Okay? So in other words, what this is basically saying is that even if I was to use infinite area for my converter, there's basically a maximum efficiency you can actually get. Okay? And that maximum efficiency is really set by the characteristics of your capacitor technology. And in particular, it's really set by that bottom plate parasitic relative to the main capacitance itself. So just to give you some rough example numbers, if we look at that 2-to-1 step-down converter, basically, if the parasitic capacitance is just 1% of your main capacitance, that immediately already says that your loss is 10% of the power that you're delivering. Okay? So that really does say that even if you don't care about the power density, meaning that you're willing to spend plenty of area for this converter, then basically at some point what you really want to do is optimize your capacitor to have as low parasitics as it possibly can. And in particular, a good way to see that is that if I look, for example, at this red curve, which is something like only 2 femtofarads per micron squared for my capacitor, but which, notice, has a lower percentage of bottom plate than this blue curve, which is 10 femtofarads per micron squared, you'll notice that once I go below a certain power density level, then indeed that red 2 femtofarads per micron curve actually has better efficiency than the more dense capacitor would have. And just in case you're curious where I came up with these numbers, these are not atypical numbers for something like a metal-metal capacitor versus an MOS capacitor. Okay? So now here's where things start getting interesting from, let's say, the architectural standpoint. So if we just take some numbers from typical technologies, and in this case we took something like a 45 nanometer technology, and we look at a 2-to-1 step-down converter, then it looks like at this kind of roughly 1 watt per millimeter squared number, we can get something pretty close to about 80% efficiency or so. Okay? And again, this is in a completely standard CMOS technology. So when I first ran these numbers, I was actually fairly shocked, because in many ways, this is actually a really, really promising result. Because if you remember, I said that those mobile devices, they're only operating at about that 100 milliwatts per millimeter squared or so. This basically says that indeed, I can basically deliver 10 times as much power density from my converter as the load itself is really demanding. Which means that indeed, I have a great opportunity to potentially just integrate this into where the decap would have been sitting in any case. Okay? But especially if you like the inductor-based topologies, there is one big caveat here, which is I'm sort of sweeping something under the rug so far, which is I've only mentioned this one particular conversion ratio, right? And remember, the whole reason we did this was because we wanted to do many different voltages on the die, not just one. Okay? So the question now is going to be, how are you going to handle multiple different or variable voltages at the output? So in order to do that, that's really, again, where I'm going to leverage the fact that this is indeed a fully integrated design. So the basic thing we have to do is to be able to support, at least efficiently, those different output voltages, then we basically need to come up with multiple different topologies. Okay? Turns out the simplest way to do that is essentially to come up with what we like to call a standard cell, which is essentially a capacitor with these 5 switches around it, where depending upon which of these switches we turn on and off in which clock phase, we can essentially configure the converter to operate in any one of a number of different topologies. So as an example, if we look at this particular design on the bottom here, this is basically done with essentially 2 of these standard cells. So in this first picture here, where, by the way, the colors represent the different clock phases, in this first picture here, I'm still just doing that 2-to-1 step-down converter. If I wanted to do, for example, a 2/3 ratio, then essentially in the first clock phase, I would connect both of these capacitors in series between the input and the output. And then in the second phase, I would essentially just stack them on top of each other. So the basic way you can kind of think of this as working is you're storing 1/3 of the input voltage on each one of those individual capacitors. And very similarly, you can kind of do the same thing for this 1/3 conversion ratio, just that you sort of reverse the order of when you stack them in series and when you put them in parallel. Okay? So if we then play that game as well, then we basically have sort of 2 or 3 knobs available to us to change the output voltage. The first is indeed just changing the topology like that. That basically gives you these sort of discrete voltage steps. And for everything in between, what I can basically do is just tune either the width of the switches or the switching frequency or both. And remember, when I'm tuning that switching frequency as an example, what I'm really just doing is changing that effective series resistance of the converter. So in other words, it's basically just doing something like linear regulation, where the efficiency you get there is just proportional to the output voltage divided by the ideal output voltage of the converter. So that's kind of where these curves come from. Each of these discrete peak points, that's kind of the best possible you can get from that particular topology. And then as you roll off in this direction, that's again just me linearly regulating down from that point, okay? The good news here is that you probably don't need something like, 40 or 50 different topologies. So you can imagine I can start filling in all of these things with little, humps in between. But at some point, practically, it's not really going to improve your overall efficiency all that much. And in fact, for most of the things we've looked at, it seems like 4 to 5 topologies is probably going to be sufficient for the range of voltages that most people are interested in. And in particular, something like about, maybe half a volt up to about 1.2, 1.3-ish volts or so, okay? That's not to say that doing these designs with even 4 or 5 topologies is very easy. In fact, one of the biggest challenges is how you deal with those power switches. But trust me, there's clever circuit designs you can come up with that deal with those problems reasonably well. So, of course, especially since my background is more on the circuit design side of things, I don't believe anything until I've actually built it in hardware, so we wanted to get some real measurements. So this was a prototype that we built, actually in collaboration with AMD, in a 32 nanometer SOI test chip. Again, no changes to the process, just using the standard digital process that was existing already. All the capacitors were built essentially out of the MOS transistors. And again, in order to reduce the ripple, we actually used 32-way interleaving in this particular design. And it also happened to use essentially the 3 different topologies I had mentioned earlier in order to allow to have this wider output voltage range. And if you're interested in some more of the details, this is actually going to be published in JSC, but is already available on the web in September of this year. So the first thing we want to do is just check, is essentially our analytical models of what it's possible to achieve from a power density versus efficiency standpoint really correct? And the long story short is that indeed, it looks like what we're able to get in the hardware matches very, very closely with what we were predicting. So roughly speaking, we're able to get about that 80% efficiency at, okay, not quite a watt per millimeter squared, but very, very close. Okay, so about this 0.86 watts per millimeter squared. And just because it's an interesting number to sort of have an understanding of, I'm also showing you here what the actual optimum switching frequency is. As you can imagine, as you change the power density, and in particular as you lower the power density, you'll switch at a lower frequency because you can tolerate a higher output resistance. But even at the very highest end, you're still talking about something like 200 to 300 megahertz or so in terms of those switching frequencies. We, of course, also wanted to verify that indeed this works in all of the different topologies. The previous plot was shown for the 2-to-1 step-down ratio. Good news is all 3 of the topologies actually worked, but if you pay close attention, you'll see this sort of measured curve for the efficiency of the 3-to-1 is not quite what we had predicted. There's actually a very sort of simple reason for that, which is that these were 32 nanometer SOI transistors with a 2-volt input supply. And if you really start generating something like, half a volt or so at the output, there's a bunch of transistors in there that have about 1.5 volts of stress on them. So basically, we were a little bit too aggressive with the switches there. They were starting to break down, which is why this efficiency basically sucked. But if you really want to do it, there's some fairly straightforward techniques you should apply to essentially fix that. Nonetheless, we were still, with these 2 topologies, able to get greater than about 70% efficiency across this roughly 0.75 to 1.15 volt output voltage range, which again actually covers pretty nicely the range of voltages that most people are interested in using these days. So overall, I think these results are actually quite promising, particularly in the sort of mobile application type of space. But I did want to say a couple thoughts about what are some of the steps we could take moving forward. The first one is that when and if 2.5 and 3D integration becomes really a mainstream type of approach, then I think there's actually a very big advantage for that with this switch capacitor type of design. And the reason for that is that if I really have this entire additional die that from a mechanical standpoint most likely has to be very similar size as to the main die itself, that basically means that I can use that entire die space right there in that interposer layer for my switch capacitor converter, okay? In other words, I've really mitigated that efficiency versus power density trade-off because now instead of needing to be 10 times more dense than my load itself, I only need to maybe be something like 1-to-1 or so. Okay, and as you noticed, I could already do about a watt per millimeter squared, which is basically the highest power density chips that I know of in terms of the load itself. Now you may think, well, isn't this immediately going to like double or even more my cost? Perhaps not, because it turns out the converter itself can actually use an older, lower cost technology. So something like 130 nanometers would actually give you very, very similar numbers to what I was already quoting you before, and you can work that out based on sort of the switch efficiency and et cetera metrics that I've been pointing out earlier, okay? So again, that's pretty promising because it says that there may indeed be a fairly low-cost way of satisfying the needs of even the highest performance processors. The other sort of interesting opportunity is that, of course, if somebody does come around and give you a more dense capacitor, for example, some of the deep trenches that Steve had been mentioning earlier, then indeed that would immediately increase either the efficiency or the power density that you can achieve. So just to give you an example, if you take some rough numbers from sort of the deep trenches that IBM indeed has developed, you can get very substantial improvements in both the efficiency and the achievable power density. And again, you don't have to take my word from sort of the analysis. This was actually demonstrated by Leland Chang at VLSI 2010, where they were able to get sort of up in this 2.3 amps per millimeter squared at about 90% efficiency or so. Now, this is again with just that 2-to-1 topology, but you can actually run the numbers for the other ratios as well, and indeed seems to maintain a fairly substantial advantage. The other really interesting opportunity here is that many people are really thinking about moving to essentially topologies where the DRAM is really closely integrated with the processor, perhaps in this stacked type of design. Well, hey, guess what? DRAMs indeed have exactly these extremely dense capacitors that I would like to use for my power conversion. So indeed, if we can convince the DRAM manufacturers that, hey, they should be building power converters as well, then actually we could potentially even integrate those into the DRAM chip, and again, at very, very minimal power area overhead, because if I can do this 10 watts per millimeter squared, basically you'd be fitting that in something like 10% of the area of the processor chip itself. So with that, I just wanted to briefly summarize. And as I think you've heard several times this morning already, there's a very clear need for fully integrated DC to DC converters, because basically using multiple off-chip supplies is too costly either from a sheer sort of component count standpoint or from the standpoint of the impedance that you get distributing into your chip. So really the main take-home message that I'd like to give here is that if you look at what switch capacitor converters can achieve, even in standard CMOS processes, I think the numbers are really quite promising. So again, we can get something on the order of this 80% efficiency or so at about a watt per millimeter squared, and maintain greater than 70% efficiency across this roughly 0.75 to 1.15 voltage output range. And this is with doing a real voltage step down. So not going from, let's say, 1 volt to this. This is actually coming all the way down from about 2 volts. And again, I'm really quite excited about this because I think there's actually existing low-cost technologies, so things like silicon interposers and DRAM capacitors, which will enable us to get to even higher both efficiency and power density numbers. So with that, I'd like to thank you all for your attention, and I'm happy to take any questions you may have.
Hi. You mentioned you may replace the area which has been used for the decoupling capacitance with the switching capacitance. But is that really equivalent? Because in this case, switching capacitance is basically feeding the DC component, while the decoupling capacitance usually just feeds a very transient current. So I'm just wondering, is that really replaceable?
Yeah, so it's a great question. Now, the thing to remember is that, especially for the topologies that I was talking about, so let's really look at something like this simple example where I just have two-phase interleaving, okay? So if I look at this example, then at any one time, one of these capacitors will be connected from V out to ground. The other one will be connected from V out to V in, okay? Now, this capacitor that's connected from V out to ground is a decoupling capacitor. Right? There's no difference between that and a normal decoupling capacitor, because after all a decoupling capacitor is a cap between V out and ground. Okay, now, there is some resistance from the switches and things like that, so there's a little bit of a loss there. But you can immediately see that in this example, half of my capacitance is exactly just like a decap would have been. Okay? So to be totally accurate, this cap that's between V in and V out is not exactly like a decap because there's some series inductance and et cetera in that input supply. But basically the equivalence holds to within essentially a factor of 2. And you can argue about is it exactly a factor of 2 or somewhere around there, but basically it holds to within a factor of 2.
Thanks.
Yeah.
Todd Besnick, Quantum. I'm going to feel like the student that asked the stupid obvious question here. why are we talking about 0.85 watts per millimeter squared when we have to dissipate that energy also? And what have people told you about? Can you summarize, or did you ignore that on purpose?
Yeah, no. So let me maybe take a step back just to make sure that I understand the question correctly, and then I'll try and answer it. So when I quote that 0.86 or 1 watt per millimeter squared, what that means is how much power is delivered from the converter to the load, okay? Now, if I have, let's just make the numbers easy. If I had a 90% efficiency converter and I was delivering a watt per millimeter squared, that would basically mean that I'm dissipating about 100 milliwatts in the converter. So in other words, if I looked at the total thermal dissipation of the chip, if without the converter I had a watt per millimeter squared, then indeed now I would have 1.1 watts per millimeter squared. So does that sort of get at the question that you're asking?
Yeah, and so then when you're covering up part of the area of the chip that you dissipate.
So remember, if I have that 1.1 watts per millimeter squared, what I'm basically saying is that if before the chip was dissipating a watt, now all I'm doing is dissipating 1.1 as an example.
Thank you.
Yeah. Now, to be totally clear, that's not to say that there's no penalty for doing this. Indeed, let's say the thermal power dissipation would go up. But the point is that if indeed I can actually leverage this integration to give you capabilities that didn't exist before, then perhaps the overall system power would actually go down enough that moving that thermal dissipation onto the chip would actually be a net win for the overall system. All right, so if there's no more questions, I think that's the end of our session, and I think all three of the speakers will be here available afterwards. Thank you.